Hey Internet, so it seems like no technology company can talk more than like 5 minutes these days without mentioning artificial intelligence or deep learning or machine learning, right? And if you're a technologist, you might feel a little bit left behind if you don't fully understand how deep learning really works and what it can and cannot do. Well, I'm here to help, so in the rest of this video we're going to go all the way from concepts to hands-on examples with deep learning, and you're going to be writing your own code in Python to solve real-world problems, so let's dive in and get started. So first things first, let's do some housekeeping. Some of you may be taking this section on deep learning and neural networks out of context from the larger data science and machine learning course that it's a part of. Maybe you just skipped ahead to this section, or maybe you're getting it on YouTube or something like that. If so, this is how to get the course materials that you need for this section of the course. Just head on over to sundog-education.com/deep-learning. Just like that. Pay attention to the dashes and capitalization and all that stuff. It all matters. And it should bring you to this page right here. From here, you can find this link for the course materials. This contains all of the scripts that are used in this section of the course. It's a zip archive, so if you need a unzip utility, which you might on Mac OS, you need to install that first to decompress that file that you get. And there's also a link here to the course slides if you want to keep those around for future reference as well. There's also a Facebook group for the larger course on data science and machine learning. You're welcome to join us there if you want to. It's completely optional. Just a place for students to hang out and learn from each other. And finally, if you are just diving into this right now, you will need a IPython 3 environment to work within. The one I use is called Nthought Canopy, and I've got a download link to it here. It is free software. But just make sure that you have a Python 3.5 or newer Python environment that supports Jupyter notebooks or IPython notebooks, as they might also be called. If you want to use Anaconda or something like that, it's totally fine. But if you don't have an existing scientific Python 3 system set up and installed on your computer, you can go ahead and download it from there. And just go ahead and install that, follow the instructions. There's nothing special about it at all. So that's all you need to get started. With that, let's talk about some prerequisites for understanding the mathematics of deep learning. Let's talk about some of the mathematical prerequisites that you need to understand deep learning. It's probably going to be the most challenging part of the course, actually, just some of the mathematical jargon that we need to familiarize ourselves with. But once we have these basic concepts down, we can talk about them a little bit more easily. I think you'll find that artificial intelligence itself is actually a very intuitive field. And once you get these basic concepts down, it's very easy to talk about and very easy to comprehend. First thing we want to talk about is gradient descent. This is basically a machine learning optimization technique for trying to find the most optimal set of parameters for a given problem. So what we're plotting here basically is some sort of cost function, some measurement of the error of your learning system. And this applies to machine learning in general, right? Like you're going to have some sort of function that defines how close to the result you want your model produces results for, right? So we're always doing, in the context of supervised learning, we will be feeding our algorithm, our model, if you will, a group of parameters, some sort of ways that we have tuned the model. And we need to identify different values of those parameters that produce the optimal results. So the idea with gradient descent is that you just pick some point at random, and each one of these dots represents some set of parameters to your model. Maybe it's, the various parameters for some model we've talked about before, or maybe it's the exact weights within your neural network. Whatever it is, we're going to try some set of parameters to start with. And we will then measure whatever the error is that produces on our system. And then what we do is we move on down the curve here, right? So we might try a different set of parameters here, again, just sort of like moving in a given direction with different parameter values, and we then measure the error that we get from that. And in this case, we actually achieved less error by trying this new set of parameters. So we say, okay, I think we're heading in the right direction here. Let's change them even more in the same way. And we just keep on doing this at different steps until finally we hit the bottom of a curve here, and our error starts to increase after that point. So at that point, we'll know that we actually hit the bottom of this gradient. So you understand the nature of the term here, gradient descent. Basically, we're picking some point at random with a given set of parameters that we measure the error for, and we keep on, pushing those parameters in a given direction until the error minimizes itself and starts to come back up to some other value. Okay, and that's how gradient descent works in a nutshell. I'm not going to get into all the hardcore mathematics of it all. The concept is what's important here, because gradient descent is how we actually train our neural networks to find an optimal solution. Now you can see there are some areas of improvement here for this idea. First of all, you can actually think of this as sort of a ball rolling downhill. So one optimization that we'll talk about later is using the concept of momentum. You can actually have that ball gain speed as it goes down the hill here, if you will, and slow down as it reaches the bottom and, kind of bottoms out there. That's a way to make it converge more quickly. when you're doing things, and that can make actual training your neural networks even faster. Another thing worth talking about is the concept of local minima. So what if I randomly picked a point that ended up over here on this curve? I might end up settling into this minima here, which isn't actually the point of the least error. The point of the least error in this graph is over here. That's a problem. That's a general problem in gradient descent. How do you make sure that you don't get stuck in what's called a local minima? Because if you just look at this part of the graph, that looks like the optimal solution. And if I just happen to start over here, that's where I'm going to get stuck. Now, there are various ways of dealing with this problem. Obviously, you could start from different locations to try to prevent that sort of a thing. But in practical terms, it turns out that local minima aren't really that big of a deal when it comes to training neural networks. This just doesn't really happen that often. You don't end up with shapes like this in practice. So we can get away with not worrying about that as much. That's a very important, good thing, because for a long time, people believe that AI would be limited by this local minima effect, and in practice, it's really not that big of a deal. Another concept we need to familiarize ourselves with is something called AutoDiff. And we don't really need to go into the hardcore mathematics of how AutoDiff works. We just need to know what it is and why it's important. So when you're doing gradient descent, somehow you need to know what the gradient is, right? So we need to measure what is the slope that we're taking along our cost function, our measurement of error, or it might be mean standard error for all we know. And to do that mathematically, you need to get into calculus, right? If you're trying to find the slope of a curve and you're dealing with multiple parameters, then we're talking about partial derivatives, right? The first partial derivatives to figure out the slope that we're heading in. Now, it turns out that this is very mathematically intensive and inefficient for computers to do. So by just, doing the brute force approach to gradient descent, that gets very expensive very quickly. AutoDiff is a technique for speeding that up. So specifically, we use something called reverse mode AutoDiff. And what you need to know is that it can compute all the partial derivatives you need just by traversing your graph in the number of outputs plus one that you have. And this works out really well in neural networks, because in a neural network, you tend to have artificial neurons that have very many inputs, but probably only one output, or very few outputs in comparison to the inputs. So this turns out to be a pretty good little calculus trick. It's complicated. You can look up how it works. It is pretty hardcore stuff, but it works, and that's what's important. And what's also important is that it's what the TensorFlow library uses under the hood to implement its gradient descent. So again, you're never going to have to actually implement gradient descent from scratch or implement AutoDiff from scratch. These are all baked into the libraries that we're using, libraries such as TensorFlow for doing deep learning. But they are terms that we throw around a lot, so it's important that you at least know what they are and why they're important. So just to back up a little bit, gradient descent is the technique we're using to find the local minima of the error that we're trying to optimize for, given a certain set of parameters. And AutoDiff is a way of accelerating that process so we don't have to do quite as much math or quite as much computation to actually measure that gradient of the gradient descent. One other thing we need to talk about is Softmax. Again, the mathematics aren't so complicated here, but again, what's really important is understanding what it is and what it's for. So basically, when you have the end result of a neural network, you end up with a bunch of what we call weights that come out of the neural network at the end. So how do we make use of that? How do we make practical use of the output of our neural networks? Well, that's where Softmax comes in. Basically, it converts each of the final weights that come out of your neural network into a probability. So if you're trying to classify something in your neural network, like, for example, decide if an image is a picture of a face or a picture of a dog or a picture of a stop sign, you might use Softmax at the end to convert those final outputs of the neurons into probabilities for each class. Okay, and then you can just pick the class that has the highest probability. So it's just a way of normalizing things, if you will, into a comparable range, and in such a manner that if you actually choose the highest value of the Softmax function from the various outputs, you end up with the best choice of classification at the end of the day. So it's just a way of converting the final output of your neural network to an actual answer for a classification problem. So again, you might have the example of a neural network that's trying to drive your car for you, and it needs to identify pictures of stop signs or yield signs or traffic lights. You might use Softmax at the end of some neural network that will take your image and classify it as one of those sign types, right? So again, just to recap, gradient descent, an algorithm for minimizing error over multiple steps. Basically, we start at some random set of parameters, measure the error, move those parameters in a given direction, see if that results in more error or less error, and just try to move in the direction of minimizing error until we find the actual bottom of the curve there, where we have a set of parameters that minimizes the error of whatever it is you're trying to do. AutoDiff is just a calculus trick for making gradient descent faster. It makes it easier to find the gradients in gradient descent just by using some calculus trickery. And Softmax is just something we apply on top of our neural network at the very end to convert the final output of our neural network to an actual choice of classification, given several classification types to choose from. Okay, so those are the basic mathematical terms or algorithmic terms that you need to understand to talk about artificial neural networks. So with that under our belt, let's talk about artificial neural networks next. Let's dive into artificial neural networks and how they work at a high level. Later on, we'll actually get our hands dirty and actually create some, but first we need to understand how they work and where they came from. So it's pretty cool stuff. I mean, this whole field of artificial intelligence is based on an understanding of how our own brains work. So, over millions of years of evolution, nature has come up with a way to make us think. And if we just reverse engineer the way that our brains work, we can get some insights on how to make machines that think. So within your brain, specifically your cerebral cortex, which is where all of your thinking happens, you have a bunch of neurons. These are individual nerve cells, and they are connected to each other via axons and dendrites. You can think of these as connections, wires, if you will, that connect different axons together. Now, an individual neuron will fire or send a signal to all the neurons it is connected to when enough of its input signals are activated. So at the individual neuron level, it's a very simple mechanism. You just have this cell, this neuron, that has a bunch of input signals coming into it, and if enough of those input signals reach a certain threshold, it will in turn fire off a set of signals to the neurons that it in turn is connected to as well. But when you start to have many, many, many of these neurons connected together in many, many different ways with different strengths between each connection, things get very complicated. So this is kind of the definition of emergent behavior. You have a very simple concept, a very simple model, but when you stack enough of them together, you can create very complex behavior at the end of the day. And this can yield learning behavior. This actually works. And it not only works in your brain, it works in our computers as well. Now think about the scale of your brain. You have billions of neurons, each of them with thousands of connections. And that's what it takes to actually create a human mind. And this is a scale that, we can still only dream about in the field of deep learning and artificial intelligence, but it's the same basic concept. You just have a bunch of neurons with a bunch of connections that individually behave very simply, but once you get enough of them together, wired in enough complex ways, you can actually create very complex thoughts, if you will, and even consciousness. The plasticity of your brain is basically tuning where those connections go to and how strong each one is. And that's where all the magic happens, if you will. Furthermore, if we look deeper into the biology of your brain, you can see that within your cortex, neurons seem to be arranged into stacks or cortical columns that process information in parallel. So for example, in your visual cortex, different areas of what you see might be getting processed in parallel by different columns or cortical columns of neurons. Now each one of these columns is in turn made of these mini columns of around 100 neurons per mini column that are then organized into these larger hypercolumns. And within your cortex, there are about 100 million of these mini columns. So again, they just add up quickly. Now, coincidentally, this is a similar architecture to how the video card, the 3D video card on your computer works. It has a bunch of very simple, very small processing units that are responsible for computing how little groups of pixels on your screen are computed at the end of the day. And it just so happens that that's a very useful architecture for mimicking how your brain works. So it's sort of a happy accident that the research that's happened to make video games behave really quickly or play Call of Duty or whatever it is that you like to play lent itself to the same technology that made artificial intelligence possible on a grand scale and at low cost. The same video cards you're using to play your video games can also be used to perform deep learning and create artificial neural networks. Think about how better it would be if we actually made chips that were purpose-built specifically for simulating artificial neural networks. Well, it turns out some people are designing chips like that right now. By the time you watch this, they might even be reality. I think Google's working on one as we speak. So at one point, someone said, hey, the way we think neurons work is pretty simple. It actually wouldn't be too hard to actually replicate that ourselves and maybe try to build our own brain. And this idea goes all the way back to 1943. People just proposed a very simple architecture where if you have an artificial neuron, maybe you can set up an architecture where that artificial neuron fires if more than a certain number of its input connections are active. And when they thought about this more deeply in a computer science context, people realize that you can actually create logical expressions, Boolean expressions, by doing this. So depending on the number of connections coming from each input neuron and whether each connection activates or suppresses a neuron, you can actually do both. That works that way in nature as well. You can do different logical operations. So this particular diagram is implementing an OR operation. So imagine that our threshold for our neuron was that if you have 2 or more inputs active, you will in turn fire off a signal. In this setup here, we have 2 connections to neuron A and 2 connections coming in from neuron B. If either of those neurons produce an input signal, that will actually cause neuron C to fire. So you can see we've created an OR relationship here where if either neuron A or neuron B feeds neuron C 2 input signals, that will cause neuron C to fire and produce a true output. So we've implemented here the Boolean operation C equals A or B, just using the same wiring that happens within your own brain. And I won't go into the details, but it's also possible to implement and not in similar means. Then we started to build upon this idea. We created something called the Linear Threshold Unit, or LTU for short, in 1957. This just built on things by assigning weights to those inputs. So instead of just simple on and off switches, we now have the concept of having weights on each of those inputs as well that you can tune further. And again, this is working more toward our understanding of the biology. Different connections between different neurons may have different strengths. And we can model those strengths in terms of these weights on each input coming into our artificial neuron. We're also going to have the output be given by a step function. So this is similar in spirit to how we were using it before, but instead of saying we're going to fire if a certain number of inputs are active, well, there's no concept anymore of active or not active. There's weights coming in, and those weights could be positive or negative. So we'll say if the sum of those weights is greater than 0, we'll go ahead and fire our neuron off. If it's less than 0, we won't do anything. So just a slight adaptation to the concept of an artificial neuron here, where we're introducing weights instead of just simple binary on and off switches. So let's build upon that even further, and we'll create something called the perceptron. And a perceptron is just a layer of multiple linear threshold units. Now we're starting to get into things that can actually learn, okay? So by reinforcing weights between these LTUs that produce the behavior we want, we can create a system that learns over time how to produce the desired output. And again, this also is working more toward our growing understanding of how the brain works. Within the field of neuroscience, there's a saying that goes, cells that fire together wire together. And that's kind of speaking to the learning mechanism going on in our artificial perceptron here, where if we have weights that are leading to the desired result that we want, you can think of those weights again as strengths of connections between neurons. We can reinforce those weights over time and reward the connections that produce the behavior that we want. Okay, so you see here we have our inputs coming into weights just like we did in LTUs before, but now we have multiple LTUs gang together in a layer, and each one of those inputs gets wired to each individual neuron in that layer, okay? And we then apply a step function to each one. Maybe this will apply to, classification. Maybe this would be a perceptron that tries to classify an image into one of 3 things or something like that. Another thing we introduced here is something called the bias neutron off there on the right. And that's just something to make the mathematics work out. Sometimes you need to add in a little fixed constant value. That might be something else you can optimize for as well. So this is a perceptron. We've taken our artificial network, moved that to a linear threshold unit, and now we've put multiple linear threshold units together in a layer to create a perceptron. And already we have a system that can actually learn. You can actually try to optimize these weights, and you can see there's a lot of them at this point. If you have every one of those inputs going to every single LTU in your layer, they add up fast, and that's where the complexity of deep learning comes from. Let's take that one step further, and we'll have a multi-layer perceptron. So now instead of a single layer of perceptrons, of LTUs, we're going to have more than one. And we actually have now a hidden layer in the middle there. So you can see that our inputs are going into a layer at the bottom, the outputs are a layer at the top, and in between we have this hidden layer of additional LTUs, linear threshold units, that can perform what we call deep learning. So here we have already what we would call today a deep neural network. Now, there are challenges of training these things because they are more complex, but we'll talk about that later on. It can be done. And again, the thing to really appreciate here is just how many connections there are. So even though we only have a handful of artificial neurons here, you can see there's a lot of connections between them, and there's a lot of opportunity for optimizing the weights between each connection, okay? So that's how a multi-layer perceptron works. You can just see that, again, we have emergent behavior here. An individual linear threshold unit is a pretty simple concept, but when you put them together in these layers and you have multiple layers all wired together, you can get very complex behavior because there's a lot of different possibilities for all the weights between all those different connections. Finally, we'll talk about a modern deep neural network, and really this is all there is to it. The rest of this course we're just going to be talking about ways of implementing something like this. Okay, so all we've done here is we've replaced that step function with something better. We'll talk about alternative activation functions. This one's illustrating something called ReLU that we'll talk about later. The key point there, though, is that a step function has a lot of nasty mathematical properties, especially when you're trying to figure out their slopes and their derivatives. So it turns out that other shapes work out better and allow you to converge more quickly when you're trying to train a neural network. We'll also apply Softmax to the output, which we talked about in the previous lecture. That's just a way of converting the final outputs of our neural network, our deep neural network, into probabilities, from whence we can just choose the classification with the highest probability. And we will also train this neural network using gradient descent or some variation thereof. There are several of them to choose from. And we'll talk about that in more detail as well. Maybe that will use AutoDiff, which we also talked about earlier, to actually make that training more efficient. So that's pretty much it. In the past 5 minutes or so that we've been talking, I've given you the entire history, pretty much, of deep neural networks and deep learning. And those are the main concepts. It's not that complicated, right? That's really the beauty of it. It's emergent behavior. You have very simple building blocks, but when you put these building blocks together in interesting ways, very complex and frankly mysterious things can happen. So I get pretty psyched about this stuff. Let's dive into more details on how it actually works up next. So now that we understand the concepts of artificial neural networks and deep learning, let's mess around with it. It's surprisingly easy to do. The folks behind TensorFlow at Google have created a nice little website called playground.tensorflow.org that lets us experiment with creating our own neural networks. And you don't have to write a line of code to do it. So it's a great way to get sort of a hands-on intuitive feel of how they work. So let's dive in. So head over to playground.tensorflow.org and you should see a screen like this. You can follow along here or just watch me do it, but I definitely encourage you to play around with this yourself and get sort of a intuitive hands-on feel of how deep learning works. This is a very powerful thing if you can understand what's going on this web page. So what we're trying to do here is classify a bunch of points just based on their location in this 2D image. So this is our training data set, if you will. We have a bunch of points here, and the ones in the middle are classified as blue, and the ones on the outside are classified as orange. So our objective is to create a neural network that, given no prior knowledge, can actually figure out if a given point should be blue or orange and predict successfully which classification it should be. So think of this as our training data. Okay, we know ahead of time what the correct classifications are for each one of these points. And we're going to use this information to train our neural network to hopefully learn that stuff in the middle should be blue and stuff on the outside should be orange. Now here we have a diagram of the neural network itself, and we can play around with this. We can manipulate it. We can add layers to it, take layers out, add more neurons to layers, whatever you want to do. Let's review what's going on here. So first of all, we're selecting the data set that we want to play with. We're starting with this default one that's called circle. The inputs are simply the x and y coordinates, the vertical and horizontal position of each data point. So as our neural network is given a point to classify, all it has to work with are those two values, its horizontal position and its vertical position. And those start off as equally weighted, being horizontal or vertical. So we can define the position of any one of these points in terms of its horizontal and vertical position. For example, this point here would have a horizontal position of -1 and a vertical position of about -5. And then we feed it into our network. You can see that these input nodes have connections to each one of these 4 neurons in our hidden layer. And we can manipulate the weights between each one of these connections to create the learning that we want. Those in turn feed into 2 output neurons here that will ultimately decide which classification we want at the end of the day. So keep in mind, this is a binary classification problem. It's either blue or orange. So at the end of the day, we just need a single signal, really. And that's what comes into this output here. Let's go ahead and hit play and see what happens. What it's going to do is start a bunch of iterations where it learns from this training data. So we're going to keep feeding it input from this training data set. And as it goes, as it iterates through it, it will start to reinforce the connections that lead to the correct classifications through gradient descent or some similar mechanism, right? And if we do that enough times, it should converge to a neural network that is capable of reliably classifying these things. Let's hit play and just watch it in action. So keep your eye on that image to the right there. All right, you can see that we've already converged on a solution. I can go ahead and pause that now. And pretty cool stuff. So you can see it has successfully created this pattern where stuff that fits into this middle area here is classified as blue, and stuff on the outside is classified as orange. So we can dive into what actually happened here. The thickness of all these connections represent their weights. So you can see the individual weights that are wired between each one of these neurons. We start off here. And you can see these are more or less equally weighted. Well, not exactly equally. Some of these are kind of weak. But what it leads to is this behavior in the middle. So we start off with equally weighted x and y coordinates. Those go to this layer here. So for example, this hidden layer here, this neuron is saying, I want to weight things a little bit more heavily in this corner, okay? And things that are like in the lower left-hand corner, not so much. And then this other one is picking out stuff on the top and bottom. This one's a little bit more diagonal to the bottom right. And this one's even more bottom right heavy. And if you combine these things together, you end up with these output layers that look like this, okay? And so we end up with these two blobby things where we're sort of giving a boost to things on the right and giving a boost to things that lie within sort of this more blobby circular area. And then when we combine those together, we end up with our final output that looks like this. Now this might look different from run to run. You know, there is some randomness to how this is all initialized. Do we actually even need a deep neural network to do this though? One optimization thing is to remove layers and see if you can get away with it. Maybe we don't even need deep learning. I mean, really, this is kind of a simple thing. You know, stuff in the middle is blue, stuff on the outside is orange. Let's go ahead and remove one of these neurons from the output layer. Again, all we need is a binary result anyway. Can it still work? It does. In fact, it's just as quick. So do I even need that layer at all? Let's go ahead and remove that final layer at all. Still works, right? So for this very basic problem, I don't even need to do deep learning. All I have here is a single layer. So this is just, it's not even a multi-layer perceptron. It's just a perceptron. Do I even need 4 neurons in there? Well, I think maybe I do, but this one here isn't really doing much, right? All it's doing is basically doing a pass-through, and the inputs coming into it have been weighted down to pretty much nothing, so I bet I don't even need that one. Let's get rid of it. It still works. Isn't that kind of cool? I mean, think about that. We only have 3 artificial neurons, and that's all it takes to do this problem. I mean, compare that to the billions of neurons that exist inside your head. Now, we probably can't get away with less than that. Let's go ahead and try to do 2 neurons and see what happens. Yeah, that's just not going to happen, right? So for this particular problem, all you need is 3 neurons. 2 won't cut it. Let's play around some more. Let's try a more challenging data set, okay? So here's a spiral pattern. And you can tell this is going to be harder because we can't just say stuff in this corner is going to be this, this classification. Like, we need a much more finer-grained way of like identifying these individual spirals. And again, we're going to see if we can just train a neural network to figure that rule out on its own. And, well, obviously 2 neurons won't cut it. Let's go back to 4. Let's see if that's enough. I bet it isn't. Yeah, you can see it's trying, but it's really struggling. We can let this run for a while, and you can see it's starting to kind of get there. You know, the blue areas are converging on some blue areas, and it's really trying hard, but it's just not enough neurons to pull this one off. Let's go ahead and add another layer. Let's see if that helps. You can see it's doing more complicated things now that it has more neurons to work with, but still can't quite get to where it needs to be. Let's add a couple more neurons to each layer. Generally speaking, you can either add more neurons to a layer or add more layers. It's going to produce the same results, but it might affect the speed in which it converges, depending on which approach you take. It's just fascinating watching this work, isn't it? All right, this one got stuck. It still can't quite pull it off. Let's add one more layer. This is actually a very common pattern you'll see. You start off with a lot of layers at first, and you kind of like narrow them down as you go. Okay, so we're going to go to a initial input layer of 6 neurons to a hidden layer of 4 neurons, and then a layer of 2 neurons, which will ultimately produce a binary output at the end. Ooh, I think it's getting there. Here we go. Wow. Okay, so technically, I mean, it's still kind of like refining itself, but it kind of did it, right? I mean, now this is what we would call overfitting to some extent, you know? I mean, obviously it has these like tendrils that are kind of cutting through here, and that's not really part of the pattern we're looking for. It's still going though. Those tendrils are kind of getting weaker and weaker. So, you know, it still doesn't have quite enough neurons to do exactly the thing that we would do intuitively. But I mean, still, I mean, this is a pretty complicated classification problem. It figured it out. It may be overfitting a little bit, but it figured it out. And all we have is, what, 12 neurons here? I mean, that's insane, right? Now, another thing I want to talk about here, too, is that it kind of illustrates the fact that once you get into multiple layers, it becomes very hard to intuitively understand what's going on inside the neural network. This gets kind of spooky, you know? I mean, what does this shape really mean? I mean, once you have enough neurons, it's kind of hard to fit inside your own head what these patterns all really represent. I mean, the first layer is pretty straightforward. You know, it's basically breaking up the image into different sections. But as you get into these hidden layers, things start to get a little bit weird as they get combined together. Let's go ahead and add one more, shall we? Actually, let's add 2 more to this output layer and add 1 more layer at the end. Let's see if that helps things converge a little bit more quickly. Yeah. All right, starting to struggle a little bit. See that? Like, it's actually got a spiral shape going on here now. So with those extra neurons, it was able to do something more interesting. We still have this this little spike here that's doing the wrong thing, and it can't seem to quite think its way out of that one. If you gave it a few more neurons, though, it might be able to figure it out. These ones are also misclassified, but I find it interesting that it actually created a spiral pattern here on its own. So maybe with a few more neurons or 1 more layer, you could actually create an even better solution. But I will leave that as an exercise for you. Now that you know how to play around with this, I really encourage you to just mess around with it and see what kind of results you can get. This spiral pattern is, in particular, an interesting problem. Just to explain some of the other parameters here, we're doing a classification here. That's what we're going to be doing throughout this section. The activation function, we talked about not using a step function and using something else. Some other ones that are popular, ReLU is actually very popular right now. Realization function we haven't talked about yet. The learning rate is just basically the step size in the gradient descents that we're doing. So you can adjust that if you want to as well. Let's see if ReLU actually makes a difference. I would expect it to just, you know, affect the speed. Oh my gosh, look at that. That's pretty darn close to what we want, right? I mean, there's, apart from this little tiny spike here, which isn't really even there, there's a little bit of overfitting going there, but we have basically created that spiral shape just out of this handful of neurons. God, I could do this all day, guys, and I hope you will too. You know, just play around with this. It's so much fun, and it gives you such a concrete understanding of what's going under the hood. I mean, look at this hidden layer here. That's where these spiral shapes are starting to emerge and come together. And when you think about the fact that your brain works in very much the same way, it's quite literally mind-blowing. Anyway, mess around with this. It's a really great exercise, and I hope you have some fun with it. All right, I know you're probably itching to dive into some code by now, but there's a little more theory we need to cover with deep learning. I want to talk a little bit about exactly how they are trained and some tips for tuning them, now that you've had a little bit of hands-on experience with them using the TensorFlow playground. So how do you train a multi-layer perceptron? Well, it's using a technique called backpropagation. It's not that complicated, really, at a conceptual level. All we're doing is gradient descent, like we talked about before, using that mathematical trick of reverse mode AutoDiff to make it happen efficiently. For each training step, we just compute the output error for the weights that we have currently in place for each connection between each artificial neuron. And then this is where the backpropagation happens. Since there's multiple layers to deal with, we have to take that error, that is computed at the end of our neural network and backpropagate it down in the other direction, push it back through the neural network backwards. Okay, and that way we can distribute that error back through each connection all the way back to the inputs using the weights that we are currently using at this training step. Okay, so pretty simple concept. We just take the error, we use the weights that we are currently using in our neural network to backpropagate that error to individual connections. And then we can use that information to tweak the weights through gradient descent to actually try and arrive at a better value on the next pass, at the next epoch, if you will, of our training passes. So that's all backpropagation is. We run a set of weights, we measure the error, we backpropagate that error using that weights, tune things using gradient descent, try it again, and we just keep doing this over and over again until our system converges. We should talk a little bit about activation functions. So in our previous exercise using the TensorFlow playground, we were using the hyperbolic tangent activation function by default, and then we switched to something called ReLU, and we saw that the results were a little bit better. What was going on there? Well, the activation function is just the function that determines the output of a neuron given the sum of its inputs. So you take the sum of all the weights of the inputs coming into a neuron. The activation function is what takes that sum and turns it into an output signal. Now, like we talked about way back in Lecture 1, using a step function is what people did originally, but that doesn't really work with gradient descent because there is no gradient there. If it's a step function, there is no slope. It's either on or off. It's either straight across or up and down. There's no useful derivative there at all. So that's why alternative functions work a little bit better in practice. There are some other ones called the logistic function, the hyperbolic tangent function. That produces more of a curvy curve. If you think about what a hyperbolic tangent looks like, it's more of a it doesn't have that sharp cutoff there at 0 at the origin, so that can work out pretty well. There's also something called the exponential linear unit, which is also a little bit more curvy. What we ended up using, though, was ReLU. That stands for rectified linear unit, and that's what this graph here is showing. Basically, it's 0 if it's less than 0, and if it's greater than 0, it climbs up at a 45-degree angle. So it's just, giving you the actual sum of the input weights as its output if that output is greater than 0. Okay, so the advantage that ReLU has is that it's very simple, very easy and very fast to compute. So if you're worried about converging quickly and you're computing resources, ReLU is a really good choice. Now there are variants of ReLU that work even better if you don't care so much about efficiency. One is called leaky ReLU. And all that is instead of being flat left of 0, it actually has a little bit of a slope there as well, a very small slope. And again, that's for mathematical purposes to have an actual meaningful derivative there to work with. So that can provide even better convergence. It's also something called noisy ReLU, which can also help with convergence. But these days, ELU, the exponential linear unit, will often produce faster learning. That's kind of it's gaining popularity now that computing resources are becoming less and less of a concern, now that you can actually do deep learning over a cluster of PCs on a network in the cloud. So that's what activation functions are all about. You can also choose different optimization functions. We've talked in very general terms about gradient descent, but there are various variations of gradient descent that you can use as well. We talked a little bit earlier about momentum optimization. Basically, the idea there is to speed things up as you're going down a hill and slow things down as you start to approach that minima. So it's a way of just making the gradient descent happen faster by kind of skipping over those steeper parts of your learning curve. Wow, I never used the word learning curve in the context where it actually means something mathematically meaningful. But anyway, there's also something called the Nesterov accelerated gradient, which is just a tweak on top of momentum optimization. Basically, it's looking ahead a little bit to the gradient in front of you to take that information into account, so that works even better. There's also something called RMS prop, which is just using an adaptive learning rate. That, again, helps point you in the right direction toward the minimum. If you remember back to how gradient descent works, it's not always obvious which direction you're going to be heading in given a change in parameters. So RMS prop is just a more sophisticated way of trying to figure out the right direction. Finally, there's something called ADAM. It stands for Adaptive Moment Estimation. Basically, it's the momentum optimizer and RMS prop combined. Kind of gives you the best of both worlds. And that is a popular choice today because it works really well and it's very easy to use. Again, the libraries you're going to use for this stuff are very high level and very easy to use. So it's not like you're going to have to implement Nesterov accelerated gradient from scratch. You're just going to say optimizer equals ADAM and be done with it. It's just a matter of choosing the one that makes sense for what you're trying to do. Make your own trade-offs between speed of convergence and computational resources and time required to actually do that convergence. Let's talk about overfitting as well. You can see you'll often end up with patterns like this where, you're not really getting a clean solution. You end up with like these weird spikes sometimes. And sometimes if you let things go a little bit too long, it ends up reinforcing those spikes, those overfitted areas where you're not really fitting to the pattern you're looking for. You're just fitting to the training data that you were given. Okay, so there are ways to combat that. And obviously, if you have thousands of weights to tune, those connections between each neuron and each layer of your neurons can add up really quickly. So it is very easy for overfitting to happen. There are ways to deal with it. One is called early stopping. So as soon as you see performance start to drop, that might be nature's way of telling you that it might be time for you to stop learning. At this point, maybe you're just overfitting. There are also regularization terms you can add to the cost function during training. That can basically like the bias term that we talked about earlier, that can help too. But a surprisingly effective technique is called dropout. And again, it's an example of a very simple idea that is very effective. The idea is just to ignore, say, half of the neurons randomly at each training step. Pretend that they don't exist at all. And the reason this works is because it forces your model to spread out its learning. If basically you're taking away half of its brain, if you will, at each training step, you're going to force the remaining half of those neurons to do as much work as possible. So this prevents things where you have individual neurons taking on more of the work than they should. You even saw in some of the examples that we ran in the TensorFlow playground that sometimes we'd end up with neurons that were barely used at all. And by using dropout, that would have forced that neuron to have been used more effectively. So very simple concept, but very effective in making sure that you're making full use of your neural network. Let's talk about tuning your topology. Another way to improve the results of your deep learning network is to just play games with how many neurons you have and how many layers of neurons you have. One way of dealing with it is just trial and error. It's kind of what we did in TensorFlow Playground. But, there can be a methodology to that even. You can start off with the strategy of evaluating a smaller network with less neurons in the hidden layers, or you can evaluate a larger network with more layers. So basically, you want to see, can I get away with a smaller network and still get good results? And just keep on making it smaller and smaller until you find the smallest it can be safely. Or you can try to make your network larger and larger and see, at what point it stops providing more benefits to you. So, just start sizing things differently and see what works and what doesn't. Again, there's sort of a spooky aspect to how this stuff all works together. It's very hard to understand intuitively what's going on inside of a neural network, a deep learning network in particular. So sometimes you just have to use your intuition to try to tune the thing and get at the right number of resources you need. Also, again, in today's modern computing environments, sometimes you don't really care so much. It's probably okay to have a deep neural network that has more neurons that it really needs, right? I mean, what's the real expense involved in that these days? Probably not much. I will say that more layers will often yield faster learning than having more neurons and less layers. So if you care about speed of convergence, adding more layers is often the right thing to do. Or you can also use something called model zoos. There are actually libraries out there of neural network topologies for specific problems. So if you don't think you're the first person in the world to solve a specific classification problem or anything else you're trying to apply a deep neural network to, maybe you should check out one of the model zoos out there to see if someone's already figured out the optimal topology for what you're trying to achieve instead of trying to reinvent the wheel. Okay, people share these things for a reason, and it can save you a lot of time. So that's enough theory, that's enough talk. In our next lecture, we'll get our hands dirty with TensorFlow and start writing some real Python code to implement our own neural networks. So if you've done any previous research in deep learning, you've probably heard of the TensorFlow library. It's a very popular framework developed by the folks at Google, and they've been kind enough to make it open source and freely available to the world. So let's talk about what TensorFlow is all about and how it can help you construct artificial neural networks. Now, the thing that kind of took me by surprise when I first encountered TensorFlow was that it's not really purpose-built for deep learning or even neural networks in general. It's a much more general-purpose tool that Google developed that just happens to be useful for developing deep learning neural networks. So more generally, it's an architecture for executing a graph of numerical operations. It's not just about neural networks. You can have any sequence of operations and define a graph of how those operations fit together. And what TensorFlow actually does is figure out how to distribute that processing across the various GPU cores on your PC or across various machines on a network and make sure that you can do massive computing problems in a distributed manner. And in that respect, it sounds a lot like Apache Spark. If you've taken any other courses from me, you've probably heard me talk about Spark. It's a very exciting technology, and Spark is also developing machine learning and AI and deep learning capabilities of its own. So in some ways, TensorFlow is a competitor to Apache Spark, but there are some key differences that we should talk about. It's not just about distributing graphs of computation across a cluster or across your GPU. It can also run on just about anything. So one thing that's special about TensorFlow is that I can even run it on my phone if I want to. It's not limited to running on computers in a cluster in some data center. And that's important because in real-world deep learning, you might want to push that processing down to the end user's device. Let's take the example of a self-driving car. You wouldn't want your car to suddenly crash into a wall just because it lost its network connection to the cloud, now would you? The way that it actually works is that you might push the actual trained neural network down to the car itself and actually execute that neural network on the computer that's running embedded within your car. Because the heavy lifting of deep learning is training that network, right? So you can do that offline, push the weights of that network down to your car, which is relatively small, and then run that neural network within your car itself. So by being able to run TensorFlow on a variety of devices, it opens up a lot of possibilities that you wouldn't have otherwise of actually doing deep learning on the edge, on the actual devices where you're trying to use it on. So that's pretty cool too. It's also written in C++ under the hood, which is also good. Whereas, Spark is written in Scala, which ultimately runs on top of a JVM. So by going down to the C++ level, that's going to give you greater efficiency with TensorFlow. But at the same time, it has a Python interface. So you can talk to it just like you would any other Python library, making it very easy to program and easy to use as a developer, but very efficient and very fast under the hood. And the other key difference between TensorFlow and something like Spark is that it can work on GPUs. GPUs, again, just being your video card, the same video card that you're using to play Call of Duty on or whatever it is you play. You can actually distribute the work across the GPU cores on your PC. And it's a very common configuration to even have multiple video cards on a single computer and actually use that to gain more performance on clusters that are purpose-built for deep learning. Plus, it's free. And it's made by Google, so it has that going for it too. Just the fact that it's made by Google has led to a lot of adoption. There are competing libraries out there to TensorFlow, but TensorFlow, as of right now, is still by and far the most popular. Installing it's really easy. All you have to do is use the pip command in your Python environment to install TensorFlow. There's also a TensorFlow-GPU package you can install instead if you do want to take advantage of GPU acceleration. If you're running this on Windows, though, I wouldn't quite go there yet. I've had some trouble getting that to work on my own Windows system. Really, you'll find that a lot of these technologies are developed primarily for Linux systems running on a cluster. So if you're running on a purpose-built computer in a cluster on EC2 or what have you that's made for deep learning, go ahead and install TensorFlow-GPU, although it's probably going to be installed for you already. So let's talk about what TensorFlow is all about. What is a tensor anyway? Well, unfortunately, this is another example of sort of fancy, pretentious terminology that people use to make themselves look smart. Yes, I'm editorializing a little bit there, but at the end of the day, a tensor is just a fancy name for an array or a matrix of values. It's just a structured collection of numbers. That's it. That's all a tensor is. So to use TensorFlow, it's a little bit counterintuitive, but it's similar to how something like Apache Spark would work too. You don't actually execute things right away. Instead, you build up a graph of how you want things to execute. And then when you're ready to execute it, you say, okay, TensorFlow, go do this. And it will go and figure out the optimal way to distribute and parallelize that work across your entire set of GPUs and computers in your cluster. So let's take a look at the world's simplest TensorFlow application here. All this is going to do is add 1 plus 2 together, okay? But it's a good illustrative example of what's actually going on under the hood. So let's see. We start by importing the TensorFlow library. We're going to refer to it as TF as a shorthand. This is all straight up Python code if you're new to Python. We'll start off by saying a equals tf.variable1 name equals a. And all that is doing is setting up a variable in TensorFlow, a variable object, which contains a single value 1, and it's going by the name of a. And the name is what will appear in visualization tools for your graph if you're using something like that. Internally, we're going to assign that to a variable in Python called a as well. So then we set up a b variable as well, that is assigned the value 2 and given the name b. And then here's where the magic starts to happen. We say f equals a plus b. And you might think that that would put the number 3 into the variable f, but it doesn't. What f actually is your graph. It's the actual connection that you're building up between the a and b tensors, okay? So f equals a plus b does not do anything except establish that relationship between a and b and their dependency together on that f graph that you're creating, okay? Now, the next thing we need to do is actually initialize those global variables. So you explicitly need to say, okay, now's the time that I want to go and put those initial values into my variables. We create an object called init, that is our global variables initializer. And then we define a session within TensorFlow. We're going to call that session S, although we're not actually going to refer to it explicitly within this block. We will take our global variables initializer object and run it. What that will do is actually stuff the values 1 and 2 inside our A and B variables. So that just initializes them to the initial variables that we defined when we created them. And then we call f.eval, and this is where computation will actually finally happen. So once we call eval on our f object, it will say, okay, I need to create a graph that takes the A variable, which contains 1, and the B variable, which contains 2, and add them together, and it will figure out how to distribute that incredibly complicated operation, I'm being sarcastic, across your entire cluster. And that will ultimately print the result 3. So we have just created the most complicated way imaginable of adding 1 plus 2 together. But, if these were larger tensors, dealing with more large data, or, for example, a huge array or a matrix of weights in a neural network, for example, that distribution becomes important, right? So although this isn't a useful exercise to do with TensorFlow, once you scale this up to the many, many connections in a big neural network, it becomes very important to be able to distribute these things effectively. So how do we extend this idea to neural networks? Well, the thing with TensorFlow, again, it's not really made explicitly for neural networks, but it can do things like matrix multiplications. And it turns out that if you think about applying all the different weights and sums that happen within a single layer of a perceptron, which we talked about earlier, you can model that as just a matrix multiplication. The way you can do that is just by taking the output of the previous layer in your multi-layer perceptron and doing a matrix multiplication with a matrix that describes the weights between each neuron of the 2 layers that you're computing, okay? And then you can add in a vector that contains the bias terms as well. So we talked about having biased neurons. Those can just be added in after the fact. So at the end of the day, you can modify this fancy diagram here of what a perceptron looks like and just model that as a matrix multiplication. So, go back and read up on your linear algebra if you want to know more about how that works mathematically. But end of the day, this is just a straightforward matrix multiplication operation with a vector addition at the end for the bias terms. So again, by using TensorFlow, we're kind of doing this the hard way. There are libraries built on top of TensorFlow that make it much simpler and more intuitive to define deep neural networks. But as we're dealing with TensorFlow at a low level, its purpose in life is really just to distribute mathematical operations on groups of numbers, on tensors. And it's up to us to sort of describe what we're trying to do in mathematical terms. But it turns out it's really not that hard to do with a neural network. Now, if we're going to actually create a complete deep learning network from end to end, there's more to it than just computing the weights between different layers of neurons, right? Like we have to actually train this thing somehow and actually run it when we're done. So the first thing we need to do is load up any training data that we have that we're going to use to train our neural network. By that, I mean data that contains the feature data that we want to train on and the target labels. So in order to train a neural network, you need to have a set of known inputs with a set of known correct answers that you can use to actually descend or converge upon the correct solution of weights that lead to the behavior that you want. We're going to construct a graph just like we did before. So kind of like before we had a graph that just added A and B variables together. We're going to introduce a new concept called a placeholder as well. And a placeholder is just a way of, having a placeholder within your graph for various data. And by doing this with a placeholder, we can use the same graph structure for both our training and for our testing and for actually applying our neural network in the future. So we can use the same placeholder for our input values and feed in our training data and do gradient descent on the resulting network. After we're done, we can use a different set of data and feed it into those same input placeholders and actually use that to test the results of our trained neural network on data that's never seen before. We will use variables, like we saw before, to keep track of the learned weights for each connection. So as we iterate through different training steps on our neural network, we're going to use variables to make sure that we have some memory in between runs of what those weights were between each connection and between each artificial neuron, and tweak those using gradient descent as we iterate through more and more training steps. After that, we need to associate some sort of an optimizer to the network as a whole. TensorFlow does make that very easy to do. It can be gradient descent or some variation thereof, such as Atom. We will then run our optimizer using our training data, and again, TensorFlow makes that pretty easy to do as well. And finally, we'll evaluate the results of our trained network using our test data set. So again, just at a high level, we're going to create a given network topology, feed it training data. I'll use gradient descent to actually converge on the optimal weights between each neuron in our network. And then when we're done, we can actually evaluate the performance of this network using a test data set that it's never seen before and see if it can correctly classify that data that it was not trained on. One other gotcha here, when you're using neural networks, it's very important to make sure that your feature data, your input data is normalized, meaning that it's all scaled into the same range. Generally speaking, you want to make sure that your input data has a mean value of 0 and unit variance. That's just the best way to make the various activation functions work out mathematically. Really, what's important, though, is that your input features are comparable in terms of magnitude. Otherwise, it's hard to combine those weights together in a meaningful way, right? I mean, your inputs are all kind of at the same level at the bottom of your neural network and feeding into that bottom layer. It's important that they're comparable in terms of magnitude. So, for example, if I were to create a neural network that tries to classify people based on their age and their income, age might range from 0 to 100, but income might range from 0 to 1,000,000. And those are wildly different ranges. So, those are going to lead to real mathematical problems if they're not scaled down to the correct range at first. Fortunately, Python's scikit-learn library has a standard scaler package that you can use to do that automatically with just one line of code. So all you have to do is remember to use it. And many data sets that you use while researching are going to be normalized to begin with. So the one we're about to use is already normalized, so we don't actually have to do that. Later on in the course, I'll show you an example of actually using standard scaler, however. And with that, let's dive in and actually try it out. We're finally at the point of the course where we're going to actually write some real code and actually build a real neural network using TensorFlow. So let's dive in our next lecture and see how it works in detail. All right, enough talking about TensorFlow. Let's actually apply it. So first thing we need to do is actually install TensorFlow itself. So if you're using the Canopy package that I've recommended for use in this course, go ahead and open that up. And if you haven't already installed TensorFlow, now is the time to do that. To do that, we can just go to the Tools menu here and open up a Canopy command prompt. If you're using Anaconda or something else, just do it from there. Within Canopy, we're going to be using the pip command to install things. So we can use pip install TensorFlow. And I've already done this previously, so it's not actually going to do anything. But if that is your first time, it will go out and actually download and install that for you. Now, depending on your operating system and environment, you might need to use a different command than pip. It might be pip3 on some platforms, but you probably know what to do there if you've installed packages before. All right, with that, let's actually open up our notebook. Go to wherever you downloaded the course materials for this course, and you should find a tensorflow.ipynb file. Go ahead and double-click that. And sometimes it takes a couple of tries to get it to work right. Hopefully we'll get lucky here. You should get a browser that opens up, and it should look something like that. Again, if you got a browser error of some sort, just open it up a second time. Sometimes things just time out and needs a second chance. Okay, so let's actually dive in and actually play with TensorFlow, shall we? Now again, TensorFlow is kind of the hard way of doing things, but it's good for you. It builds character. If you can get through this, and then you'll find the rest of this course pretty easy, I think. So let's start by looking at that world's simplest TensorFlow application that we did in the slides in the previous lecture and go ahead and see how that works. So again, if we just click in this little code block here, we've already installed TensorFlow. All we need to do is import that, and we're going to call it TF. And as we did before, we're going to create an A variable that contains the number 1 initially, a B variable that contains the number 2, and create a graph called F that just adds those two variables together. We will then create a global variables initializer, create a session in TensorFlow, run the global variables initializer to actually put the initial values of 1 and 2 into A and B respectively, and actually evaluate that graph that we actually defined to add the two things together and print the results of that. So again, world's most complicated way of adding 1 and 2 together. Let's go ahead and hit Shift-Enter to actually execute that block. And it's actually spinning up TensorFlow and figuring out how to distribute 1 plus 2 across my entire system. And sure enough, the answer is 3. So TensorFlow is working. If you got some error there, then there's some installation issue you need to go back and deal with. Let's do something a little bit more interesting than adding 1 and 2 together. We'll do some actual handwriting recognition. Now this is going to be using something called the MNIST dataset, and if you've looked at other tutorials in the field of deep learning, you might be saying, oh god, not another MNIST example. But there's a reason people use this example so much. First of all, it's built right into TensorFlow, so it's very easy to use, and it's also very fun. We're actually going to be doing handwriting recognition here. So we have this dataset that contains 70,000 handwriting samples of people writing the numbers 0 through 9, and our challenge is to predict which number each handwritten image represents, which is kind of a fun task. It's like mimicking to some extent how your brain actually recognizes handwritten numbers. And some people's handwriting is pretty bad, so sometimes this can be a challenge. Let's talk about the nature of the data. So it's broken up into a training data set and a testing data set. And each image is a 28 by 28 image of grayscale pixels. Now, for the purpose of this example, we're going to be starting things off a little bit simple. We're just going to treat each pixel as an individual input into a neural network, into a deep learning network. So we're just going to flatten each one of these images into a flat 1D array of 784 pixels. Okay, so we take the first 28 rows from the top of the image, stick the next 28 pixels from the next row, then stick on the next 28 pixels from the next row, and at the end of the day, we just have a list of 784 values that represent the grayscale value of each pixel of that 28 by 28 image, okay? It'll make more sense when we look at some examples here. Let's start by loading that up. As I said, it's built into TensorFlow itself, so all we need to do is import tensorflow.examples.tutorials.mnist. We'll create a session now because we'll need that later, obviously. We're going to create an interactive session in TensorFlow, which makes it easier to work with TensorFlow within an IPython environment like we have here. This removes the need of actually explicitly creating a session and looping within it. We want to break up this work across multiple code blocks, so that's how we do that here with an interactive session. Finally, we'll just call read datasets to actually load up the MNIST dataset. And one hot equals true. What does that mean? So at the end of the day, this neural network is going to have 10 outputs, and each one of those output will represent basically some weight of how much it thinks that individual number represents the classification of that numerical image. So one hot means that if, for example, I have the number 0, I'm going to encode that as a binary pattern. So let's skip ahead a little bit here down here where I talk about it a little bit more. For example, the number 1 would be encoded as 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. So we have this 1D array of binary values 0 or 1, and where that 1 appears indicates what the actual label of that image is. So if I have an image of the number 1 that somebody wrote, I would encode that in one hot format as a array of 10 values where the value 1 appears in value 1. So remember, we start counting at 0 in Python world. So if it were the number 0, the 1 would be there. If it were the number 2, the number 1 would be there instead. So that's what one hot encoding means. It's just a more optimal way of doing classification that's more finely tuned to the output of our neural network. Okay, so let's talk about the shape of our data. We have a training data set of 55,000 images, and then a test data set of 10,000 images that we're going to use to evaluate the performance of our neural network by giving it data that it's never seen before and measuring how well it can predict the correct classification of each image. So we say that the shape of our training data is 55,000, 784. That means we have 55,000 images, each with 784 data points within them. So again, 28 by 28 images, 28 times 28 is 784. So our input tensor shape is going to be 55,000 by 784. 55,000 images with 784 values on each image. The test data is just going to be the label data. So that will be of shape 55,010. Again, we have 55,000 input training data points, and we have our one hot encoding that is an array of 10 values, where wherever the number 1 appears represents the correct label. Okay, so more specifically here, when we talk about a shape of 55,010, that's going to be the shape of our training label data. Okay, so that's kind of what we're working toward while we're training the network. During the test phase itself, we only have 10,000 samples, so the shape of that test data would be 10,010 in that case. All right, let's take a look at our sample data here, just so we have more of an intuitive understanding of what we're up against. Very important to always understand your input data, because often there's going to be problems with your source data, outliers that you need to deal with, and you want to really understand at an intuitive level what you're up against here. So let's go ahead and display some samples here. By the way, I never actually ran this code block up here, so let's go up to code block 2 here and hit Shift-Enter to make sure that we actually read that data set in. Takes a little bit of time. There we go. All right, so that's all been imported successfully. What's going on here is we're going to create a little function called display_sample for a given input element. So when I say, for example, display_sample 1, 2, 3, 4, that means pick the 1234th input sample from our training data set and display it to me. So what we're doing here is we're going to extract the label in one hot format for that particular sample of the training data. We will convert that to a human readable number by using the argmax function. All that does is say take the array element with the largest value and display that array element's value back to me. So that's just a little quick way of converting one hot format back to a human readable digit. We will then reshape that 1D image. So remember, each value is just a flat value of 768 pixels. We take each row and just stick it next to each other. To actually visualize that as a two-dimensional image in the same way that your brain sees it, we're going to want to reshape that to a 28 by 28 2D array. And then we can use Python's built-in matplotlib library to actually display that as an image. So let's go ahead and hit that, Shift-Enter. And we can see that the training data sample 1234 actually corresponds to an image of someone drawing the number 9. Here's what the one hot input, what the one hot label data looks like there. You can see there's just a 1 in the final value that represents the value 9. And we reshaped that to 28 by 28 and displayed it as a grayscale image. So, it's not a bad example. That actually looks like a 9. So someone's handwriting was halfway decent there at least. So that's the kind of data that we're dealing with here. This is what a training data sample might look like. All we're getting as an input is this image flattened. Okay, it's actually going to be flattened and not a 2D image, along with the target label. So we know that this person intended to draw the number 9, and this is what it looked like. And we have 55,000 such samples with which we can train our neural network. Okay. Just to drive it home, though, exactly what your neural network is, quote unquote, seeing, let's go ahead and visualize what that looks like. So what this image is showing is the first 500 training samples flattened out in the same format that your neural network is going to get it. So this is stretching out over 784 numerical values for each value. So from 0 to 500, we have each individual input image flattened out into a 1D array of 784 values. So instead of constructing this as individual 2D images, which is how your brain might process it, instead we're going to create a neural network that actually tries to recognize patterns in these flattened rows instead. And we're just going to go through the first 500 here, reshape them to the 1D format that we're actually going to be feeding into our neural network, concatenate those all into a single image and display that. So you can see here we have sort of these bands that correspond to the center of the image on each row. And it's a little bit mind-blowing here. I think it's important to realize that this is the raw input into the neural network that we're going to build. So each row, this represents a training sample being fed into our neural network as we train it. And what that neural network is quote unquote seeing is just one row of that data at a time. So, your brain would have a very hard time trying to figure out, well, does this particular row represent the number 2 or not? There's no way in heck you're going to figure that out just by looking at it. But we're going to create our own little special neural network that actually does that. And later on we'll talk about how to actually do real image processing better in a way that's closer to how your brain actually processes things. But I think it's remarkable if this works at all using this sort of naive approach. All right, let's actually start writing some code to put it all together and build our graph in TensorFlow. First thing we need to do is create some placeholders for the input training data and the target labels. So we will set up a placeholder called input_images of shape none784. So what that means is that we're going to create a placeholder for the training data, or the data being input into our neural network, that has some arbitrary number of input values, input images, and each one of those images will contain 784 values. So that just defines the shape of the data that's going into our neural network. We also need to create a placeholder for the target labels, and that will have a shape of some arbitrary number of target images and a one-hot array of 10 values that we use to evaluate the actual label. So the point of doing a placeholder here is that we can reuse this same neural network for training and for testing and for actually using it in practice. So for our first pass where we're training our neural network, our input images will be assigned to our training dataset images. The target labels placeholder will be assigned to the labels of that training data set, and we will use that to actually run gradient descent and actually try to tune the weights between each neuron. Later on, when we're testing the performance of this neural network, our input images will be assigned to the images in our test data set. The target labels will be assigned to the known labels of those testing data set images, and then we can measure how well our neural network predicted the correct label versus that target label set. And if you were going to actually use this in the real world, you wouldn't be using the target labels at all. You would just assign the input images to the images that you want to classify and look at the output in target labels and see what you came up with. Moving on, we still need to run this stuff, by the way. Let's go ahead and execute that image there and see if that actually works. And in this block, we'll go ahead and set up those placeholders. Just select that block, hit Shift-Enter, and that should be all set up. Now again, nothing really happens in TensorFlow until we actually evaluate things and actually execute things. We're just sort of setting up the graph at this point. So let's go ahead and set up the topology of our neural network itself. We're going to set up a multi-layer perceptron here. We'll start off with 784 input images. So what this first line is saying is we're going to create a tensor called input underscore weights. That's going to be a variable that is normalized 784 comma hidden nodes. So that means that we're going to create a layer here that has 784 input signals. That's one for each input pixel of each image. And it's going to have an output of 512 hidden nodes going to the next layer. Okay, so this is setting up a layer of our neural network that takes 784 inputs and has outputs going to 512 inputs to the next layer. Okay, we also need to set up the input biases, which is just going to be a 1D array of the 512 hidden nodes in between. So this is going to be the bias terms on that layer between the input layer and the hidden layer. Okay, now again, in TensorFlow, we kind of have to do this all the hard way. We're just describing things in terms of linear algebra here. So we're just going to have these matrices of weights and vectors of biases that we're passing around. For the hidden layer itself, we're going to have an input of 512 and an output of 10 going to our final classification layer in one hot format. And we will also have a bias vector applied to that as well. That is 10 wide. That will be applied to the final output layer. Okay. Next, let's go ahead and hit Shift-Enter to get that set up. Next, we need to put it all together. So we're going to create an input layer that does a matrix multiplication between that input image layer and the input weights that we set up as a variable. So again, remember these input weights are a variable that will contain those weights and over time, tweak them. So it maintains memory between each training run. We will then define our hidden layer as using the ReLU activation function on the sum of that input layer's matrix multiplication and the bias vector that we set up previously. Okay. Finally, we'll compute our output layer as doing a matrix multiplication between that hidden layer's output and the weight matrix of those hidden layer, and add in that hidden bias vector of 10 as well. Okay, so just to explain better the difference between what's in this block and what's in this block, let's go ahead and hit Shift-Enter before we forget to actually set that up. What we're doing up here is creating variables to hold the weights and biases between each training run. Okay, so these are maintaining the memory of the actual weights and bias terms within our neural network from run to run. What we're doing in this block is actually defining the connections, defining the layers themselves. So we're saying here that we're going to have our input layer that uses that variable that we created for all the weights of the input values. We'll create a hidden layer that also uses the output of that input layer and the bias variables that we assign for that. We will also use the hidden weights and hidden biases variables as we define our final digit weights layer here that ultimately goes to our final classification step. Okay. Whew. Again, it's a lot to wrap your head around, but we're doing it the hard way. Remember, this is going to get easier. I promise. So again, what we've done is set up a very simple multi-layer perceptron with an input layer of 784 inputs, one for each pixel of each image. There is a hidden layer of 512 neurons that goes to an output layer of 10, which represents one hot format of the final classification. All right, next thing we need to do is set up a loss function. How do we actually measure the correctness of our results? And the way we're going to do that is by using Softmax, which we taught before. So we're going to use specifically Softmax with something called cross entropy. All that does is apply a logarithmic scale to penalize incorrect classifications more than ones that are close. So that's just a way of making things converge a little bit more quickly. We will assign the final output layer of our digit weights and use the target labels as what are the so-called correct answers that we want to converge toward. Okay, so we've created a loss function that takes a look at our final digit weights, applies Softmax to them, and compares that to the target labels in one hot format. Okay, so that's what we're going to be optimizing for. Shift-Enter. Next, we need to define an optimizer that will apply to this neural network, and we're going to just use a straight-up gradient descent optimizer. The 0.5 is the learning rate. That's something you can play with if you want to. Obviously, if it's too big, you might overshoot the actual minimum that you're looking for. If it's too small, it might take too long, and we will assign it that loss function that we just defined to actually descend upon. Shift-Enter. Finally, we need to create a function that measures the accuracy of our resulting neural network. So we will set up a function called correct prediction. And actually, this is another graph in TensorFlow that we're setting up that will just evaluate whether the argmax of the final digit weights matches the argmax of the target labels. So if the largest final weight output of our neural network matches the largest one-hot format of our target labels, that will give it a 1 value, otherwise a 0. And we will measure accuracy by taking the mean of all of those correct prediction results over all of the training data that, of all the test data that we actually measured. So Shift Enter. All right, let's actually run this thing. So all we've done up to this point is define the actual graph within TensorFlow that we're going to run. Let's go ahead and run the global variables initializer to get those initial values into it. What we're going to do now is run 2,000 training steps of 100 images on each batch, okay? So for x in range 2,000, that means that we're going to execute the following block of code 2,000 times. We will pick out the next 100 training images from our batch of training images. We will run our optimizer, so this is what actually kicks off TensorFlow and actually does some real work. And we pass in this dictionary in Python that just matches placeholders to actual data. So for this training run, we're going to assign a batch of 100 training images to the input images placeholder. And we will take the labels data in one-hot format and assign that to the target labels placeholder and let that run and be optimized. And then finally here, for every 100 steps, we'll print out what epoch we're currently on and the accuracy that we've seen. This will just let us see the progress over time, because since we didn't install the GPU accelerated version of TensorFlow, this can actually take a while. So let's go ahead and hit Shift and mistake. So let's go ahead and hit Shift Enter and kick this off. It's actually running pretty quickly. And you can see how that accuracy is getting better and better over time. Although at this point, you know, we probably could have done early stopping, because at around 92%, it's really not going to do much better. Okay, so there we have it. All right, so hey, that's not bad, but we got about 92% accuracy in correctly predicting the correct classification of a bunch of images out of the MNIST dataset. So that's kind of cool. So let's actually take a look at our test data and evaluate the performance of this thing for real. What we're going to do is go through the first 100 test images and just print out any ones that are actually incorrectly classified, so we can get a more intuitive feel of the sorts of images that our neural network is having trouble with. So we're going to go through the first 100 images, take each one. The image will be flattened to a 784 wide array of pixels, which is what our neural network expects as input. We'll also pluck out the labels as well, convert that to a human readable label using the argmax function. We will then run, using the same session that we've been using before, our neural network, using the input images of xtrain that we extracted from the test data set, and actually get the argmax result of that classification. So basically this is going through one image at a time and feeding it into our neural network and seeing if it actually matches the predicted label or not. So we'll take our prediction that comes out of the neural network here, compare that to the label that we know is the one that was correct for this image, and if it does not match, we'll print out the actual picture of the one that it got wrong. So let's run that. Interesting. So for example, here is somebody who was trying to draw the number 9 and made this thing that our system thought was a 7. Not exactly the best handwriting there. You can kind of understand how it got confused. Here's a, I guess that was supposed to be a 5. We thought it was a 6, which is really not unreasonable. This is someone trying to draw the number 2. For some reason, we thought it was a 3. It's a very messy 2. Here's someone trying to draw an 8 that we thought was a 2. And this is an example of where, you know, your human brain probably wouldn't have much of a trouble with that. But, you know, the fact that we're just trying to create a very limited neural network here that only deals with these things in a 1D fashion means that we're kind of limited in the effectiveness here. Later on, we'll talk about more techniques that can do this more efficiently. But for now, you know, it's not too bad. Anyway, some more examples here that you can look at. You can see that that's pretty clearly a 4 to me, but for some reason we thought it was a 9. So this 1D approach to learning has its limitations, but overall, it's not bad. We actually constructed a neural network that can classify the correct number that someone was trying to draw more often than not. So, hey, that's kind of cool. Anyway, let's see if you can improve upon it as an exercise. If you want to fiddle around with things, try using more hidden neurons. Try using fewer. What's the least amount that you can use before quality starts to suffer? Try adding another hidden layer. Try different batch sizes. Just mess around with things. Get your hands dirty. See if you can do a better job. Well, let's see what the best accuracy you can get from this multi-layer perceptron. Can you actually top my results? Have some fun with it. And in our next lecture, we'll talk about how to make this all a lot easier using the Keras library. So yeah, TensorFlow is not exactly easy to use. It took us over 20 minutes just to walk through the code to do the most basic deep learning example there is out there, the MNIST dataset that people generally use for tutorial purposes. Let's talk about a way to make things a lot easier using the Keras library. So what's the big deal about Keras? Well, it runs on top of TensorFlow, so it's a higher level library that's more purpose-built for deep learning. Like we said, TensorFlow is more of a general purpose tool for distributing graphs of operations across GPUs and many computers on a cluster, whereas Keras is really built for the purpose of deep learning, so it's a lot easier to use for that purpose. It's not limited to TensorFlow either. It can actually run on top of other libraries as well, such as Theano is another popular competitor to TensorFlow, but as I said, TensorFlow seems to be winning the competition here just because it's sponsored by Google. Another benefit of Keras, in addition to its ease of use, is its integration with the scikit-learn library. So if you're used to doing machine learning in Python, you've probably used scikit-learn a lot, and using Keras, you can actually integrate your deep neural networks with scikit-learn. And you might have noticed in our previous lecture that we kind of glossed over the problem of actually doing train, test, or cross-validation on our neural network because it would have been a kind of a big pain in the butt. But with scikit-learn, it's very easy to do cross-validation and perform proper analysis and evaluation of this neural network. So that makes it easier to evaluate what we're doing and to integrate it with other models or even chain a neural network with other deep learning or machine learning techniques. There's also a lot less to think about, and that means that you can often get better results without even trying. With TensorFlow, you have to think about every little detail at a linear algebra level of how these neural networks are constructed because it doesn't really natively support neural networks out of the box. You have to figure out, how do I multiply all the weights together? How do I add in the bias terms? How do I apply an optimizer to it? How do I define a loss function? Things like that, whereas Keras can take care of a lot of those details for you. So when there's less things for you to screw up, and more things that Keras can take on for you in terms of optimizing things for what you're really trying to do, often you can get better results without doing as much work, which is great. And why is that important? Well, the faster you can experiment and prototype things, the better your results will be. So if it's that much easier for you to try different layers in your neural network, different topologies, different optimizers, different variations, it's going to be that much easier and quicker for you to converge on the optimal kind of neural network for the problem you're trying to solve. Whereas if TensorFlow is putting up a bunch of roadblocks for you along the way, at the end of the day, you only have so much time to devote to these problems, right? So the more time you can spend on the topology and tuning of your neural network and the less on the implementation of it, the better your results will be at the end of the day. Now, you might find that Keras is ultimately a prototyping tool for you. It's not as fast as just going straight to TensorFlow. So, sometimes you want to converge on the topology you want and then go back and implement that at the TensorFlow layer. But again, just that ease of prototyping alone is well worth it. Makes life a whole lot easier. So let's take a closer look. Let's take a look at doing the same problem that we did in TensorFlow with Keras, and you'll see this goes a lot more quickly. So if this is your first time using Keras, first you need to install it. If you're using Nthought Canopy, you can do that by going to the Tools menu and opening up a command prompt. And just type in pip install Keras. Assuming you've already installed TensorFlow, will automatically set itself up on top of TensorFlow, and I've already installed Keras, so it's not actually going to do anything for me, but for you it will probably go out and download and set that up for you. With that out of the way, let's go back to our course materials here. You want to open up the keras.ipynb file. And up should come our browser with a notebook that looks like this. All right, so we've already installed it. And again, Keras is just a layer on top of TensorFlow that makes deep learning a lot easier. All we need to do is start off by importing the stuff that we need. So we're going to import the Keras library and some specific modules from it. We have the MNIST dataset here that we're going to experiment with, the sequential model, which is a very quick way of assembling the layers of a neural network. We're going to import the dense and dropout layers as well, so we can actually add some new things onto this neural network to make it even better and prevent overfitting. And we will import the RMS prop optimizer, which is what we're going to use for our gradient descent. Shift-Enter, and you can see we've already loaded up Keras just by importing those things. It's using TensorFlow as a backend. Let's go ahead and load up the MNIST dataset that we used in the previous example. Keras's version is a little bit different. It actually has 60,000 training samples as opposed to 55,000. Still 10,000 test samples. And that's just a one-line operation. All right, so now we need to, as before, convert this to the shape that TensorFlow expects under the hood. So we're going to reshape the training images to be 60,000 by 784. Again, we're going to still treat these as 1D images. We're going to flatten these all out into 1D rows of 784 pixels for each 28 by 28 image. We also have our test data set of 10,000 images, each with 784 pixels apiece. And we will explicitly cast the images as floating point 32-bit values, and that's just to make the libraries a little bit happier. Furthermore, we're going to normalize these things by 255. So the image data here is actually 8-bit at the source, so it's 0 to 255. So to convert that to 0 to 1, what we're doing basically here is converting it to a floating point number first from that 0 to 255 integer, and then dividing it by 255 to rescale that input data to 0 to 1. We've talked before about the importance of normalizing your input data, and that's all we're doing here. We're just taking data that started off as 8-bit 0 to 255 data and converting that to 32-bit floating point values between 0 and 1. That's all that's going on there. As before, we will convert our labels to one hot format, so that's what toCategorical does for you. It just converts the label data on both the training and the test data set to one hot 0 to 10 values. Let's go ahead and run that previous block there before we forget. And we will run this as well. Again, I'm just hitting Shift-Enter after selecting the appropriate blocks of code here. All right, as before, let's visualize some of the data just to make sure that it loaded up successfully. This is pretty much the same as the previous example. We're just going to look at our input data for sample number 1, 2, 3, 4. And we can see that our one hot label here is showing 1 in position 4, and since we start counting at 0, 0, 1, 2, 3, that indicates label 3. Using argmax, that gives us back the human readable label, and by reshaping that 768 pixel array into a 2D shape, we can see that this is somebody's attempt at drawing the number 3. Okay, so far so good. Our data looks like it makes sense and was loaded correctly. Now, you remember back in when we were dealing with TensorFlow, we had to do a whole bunch of work to set up our neural network. Well, look at how much easier it is with Keras. All we need to do is say that we're setting up a model, a sequential model, and that means that we can add individual layers to our neural network one layer at a time, sequentially, if you will. So we will start off by adding a dense layer of 512 neurons with an input shape of 784 neurons. So this is basically our first layer that takes our 784 input signals from each image, one for each pixel, and feeds it into a hidden layer of 512 neurons. And those neurons will have the ReLU activation function associated with them. So with one line of code, we've done a whole lot of work that we had to do in TensorFlow before. And then on top of that, we'll put a Softmax activation function on top of it to a final layer of 10, which will map to our final classification of what number this represents from 0 to 9. Okay? So wasn't that easy. We can even ask Keras to give us back a summary of what we set up just to make sure that things look the way that we expected. And sure enough, we have two layers here. One that has 512 and then going to a 10 neuron layer for the final classification. And this does sort of omit the input layer, but we do have that input shape of 784 features going into that first layer. All right. Now, you also might remember that it was kind of a pain in the butt to get the optimization and loss function set up in TensorFlow. Again, that's a one-liner in Keras. All we have to do is say that our loss function is categorical cross-entropy, and it will know what to do there. We're going to use the RMS prop optimizer, just for fun. We could use any other one that we wanted to. We could just use Atom if we wanted to, or there are other choices like AdaGrad, SGD. You can read up on those at this link here if you want to. And we will measure the accuracy as we go along. So that's all that's saying. Let's go ahead and hit that, and that will build the underlying graph that we want to run in TensorFlow. All right, so now we actually have to run it. And again, that's just one line of code with Keras. All we need to do is say that we're going to fit this model using this training data set. These are the input features, the input layers that we're going to train with. We want to use batch sizes of 100. We're going to run that 10 times. I'm going to set a verbosity level of 2 because that's what works best with an IPython notebook. And for validation, we will provide the test data set as well. So instead of writing this big function that does this iteration of learning by hand like we did in TensorFlow, Keras does it all for us. So let's go ahead and hit Shift-Enter and kick that off as well. Now, Keras is slower than TensorFlow, and it's doing a little bit more work under the hood, so this will take more time. But you'll see that the results are really good. I mean, even on that first iteration, we've already matched the accuracy that we got after 2,000 iterations in our hand-coded TensorFlow implementation. We're already up to epoch 6, and we're approaching 99% accuracy on our training data. Keep in mind, this is measuring the accuracy on the training data set. And we're almost there. But yeah, I mean, even with just 10 epochs, we've done a lot better than using TensorFlow. And again, you know, Keras is kind of doing a lot of the right things for you automatically without making you even think about it. That's the power of Keras. Even though it's slower, it might give you better results in less time at the end of the day. Now, here's something that we couldn't really do easily with TensorFlow. It's possible, I just didn't get into it because that lecture was long enough as it was. But remember that we can actually integrate Keras with scikit-learn. So we can just say model.evaluate, and that's just like a scikit-learn model as far as Python's concerned, and actually measure, based on our test data set, what the accuracy is. And using the test data set as a benchmark, it had a 98% success rate in correctly classifying those images. So that's not bad. Now, mind you, a lot of research goes into optimizing this MNIST dataset problem, and 98% is not really considered a good result. Like I said, later in the course, we'll talk about some better approaches that we can use. But hey, that's a lot better than we got in the previous lecture, isn't it? As before, let's go ahead and take a look at some of the ones that it got wrong, just to get a feel of where it has trouble, things that our neural network has challenges. The code here is similar. We're just going to go through the first 1,000 test images here. And since it does have a much higher accuracy rate, we have to go deeper into that test data to find examples of things that went wrong. We'll reshape each image into a flat 784 pixel array, which is what our neural network expects as input. Call Rmax on the resulting classification in one hot format and see if that predicted classification matches the actual label for that data. If not, print it out. All right, so you can see here that this model really is doing better. The ones that it's getting wrong are pretty wonky, okay? So in this case, we predicted that this was a number 9, and if I were to look at that myself, I might guess that was a 9 as well. Turns out this person was trying to draw the number 4. But, this is a case where even a human brain is starting to run into trouble as to what this person was actually trying to write. I don't know what that's supposed to be. Apparently they were trying to draw the number 4. Our best guess was the number 6. Not unreasonable given the shape of things. Here's somebody who was trying to draw a 2, but it looks a whole lot more like a 7. Again, I wouldn't be too sure about that myself. So, even though we flattened this data to one dimension, this neural network that we've constructed is already rivaling the human brain in terms of doing handwriting recognition on these numbers. I mean, that's kind of amazing. That one, I probably would have guessed a 3 on that one. But again, you can see that the quality of the stuff that it has trouble with is really sketchy. What is that? A scorpion? Apparently that was supposed to be an 8, and our best guess was a 2. But that's smudge. Wow. Okay, yeah, some people really can't write. That's a 7? Yeah, I mean, you get the point here. So just by using Keras alone, we've gotten better accuracy, we've gotten a better result because there's less for us to think about. All right, and you can probably improve on this even more. So again, as before with TensorFlow, I want you to go back and see if you can actually improve on these results. Try using a different optimizer than RMSprop. Try, different topologies. And the beauty with Keras is that it's a lot easier to try those different topologies now, right? Keras actually comes in its documentation with an example of using MNIST, and this is the actual topology that they use in their example. So go back and give that a try. See if it's actually any better or not. See if you can improve upon things. One thing you can see here is that they're actually adding dropout layers to prevent overfitting. So it's very easy to add those sorts of features here. Basically what we've done here is add that same dense layer of 512 hidden neurons, taking the 784 features, and then we're going to drop out 20% of the neurons at the next layer to force the learning to be spread out more and prevent overfitting. So might be interesting to see if that actually improves your results on the test data set by adding those dropout layers. All right, so go play with that. When we come back, we'll do some even more interesting stuff using Keras. So that was a lot easier using Keras, wasn't it? Now, the MNIST dataset is just one type of problem that you might solve with a neural network. It's what we call multi-class classification. Multi-class because the classifications we were fitting into ranged from the numbers 0 through 9. So in this case, we had 10 different possible classification values, and that makes this a multi-class classification problem. Now, based on Keras's documentation and examples, they have general advice on how to handle different types of problems. So here's an example of how they suggest setting up a multi-class classification issue in general. So you can see here that we have two hidden layers here. We have an input dimension of however many features you have coming into the system. In this example, there's 20, but depending on the nature of your problem, there may be more. It's setting up two ReLU activation function layers, each with 64 neurons each. And again, that's something that you would want to tune depending on the complexity of what you're trying to achieve. It's sticking in a dropout layer to discard half of the neurons on each training step. Again, that's to prevent overfitting. And then at the end, it's using a Softmax activation to one of, in this example, 10 different output values. Okay, so this is how they go about solving the MNIST problem within their own documentation. They then use an SGD optimizer and a categorical cross-entropy loss function. So again, you can just refer to the Keras documentation for some general starting points on where to begin from, at least when you're tackling a specific kind of problem. Again, the actual numbers of neurons, the number of layers, the number of inputs and outputs will obviously vary depending on the problem you're trying to solve. But this is the general guidance they give you on what the right loss function is to start with, what the right optimizer to start with might be. Another type of classification problem is binary classification. Maybe you're trying to decide if images are pictures of males or females. Maybe you're trying to decide if someone's political party is Democrat or Republican. If you have an either-or sort of problem, then that's what we call a binary classification problem. And you can see here their recommendation here is to use a sigmoid activation function at the end instead of softmax, because you don't really need the complexity of softmax if you're just trying to go between 0 and 1. So sigmoid is the activation function of choice in the case of binary classification. They're also recommending the RMS prop optimizer. And the loss function in this case will be binary cross-entropy in particular. So a few things that are special about doing binary classification as opposed to multiclass. Finally, I want to talk a little bit more about using Keras with scikit-learn. It does make it a lot easier to do things like cross-validation, and here's a little snippet of code of how that might look. So here's a little function that creates a model that can be used with scikit-learn. Basically, we have a create model function here that creates our actual neural network. So we're using a sequential model, putting in a dense layer with 4 inputs and 6 neurons in that layer. That feeds to another hidden layer of 4 neurons. And finally, it's going to a binary classifier at the end with a sigmoid activation function. So a little example of setting up a little binary classification neural network. We can then set up an estimator using the Keras classifier function there. And that allows us to get back an estimator that's compatible with scikit-learn. So you can see at the end there, we're actually passing that estimator into scikit-learn's cross-val score function. And that will allow scikit-learn to run your neural network just like it were any other machine learning model built into scikit-learn. So that means cross-val score can automatically train your model and then evaluate its results using k-fold cross-validation and give you a very meaningful result for how accurate it is and its ability to correctly predict the classifications for data it's never seen before. So with those snippets under our belt, let's try out a more interesting example. Let's finally move beyond the MNIST sample. What we're going to do is try to predict the political parties of congressmen just based on their votes in Congress using the Keras library. So let's try this out. So let's play some more with Keras. Open up the politicsexercise.ipynb file in your class materials here. And that should be packaged along with these House Votes data files that we're going to be playing around with here. So go ahead and double click that. And up it should come in your browser. I'm assuming you've already installed Keras. All right, and we should see something like this. Now this is actually going to be an example that I'm going to give to you to try out yourself as an exercise. So I'm going to help you load up this data and clean it up. But after that, I'm going to leave it up to you to actually implement a neural network with Keras to classify these things. So again, to back up, what we're going to do is load up some data about a bunch of congressional votes that various politicians made. And we're going to try to see if we can predict if a politician is Republican or Democrat just based on how they voted on 17 different issues. And this is older data. It's from 1984, so you definitely need to be of a certain age, shall we say, to remember what these issues were. And if you're from outside of the United States, just to give you a brief primer in U.S. politics, basically there are two main political parties in the United States, the Republicans, which tend to be more conservative, and the Democrats, which tend to be more progressive. And obviously those have changed over the years, but that's the current deal. So let's load up our sample data. I'm going to use the pandas library that's part of our scientific Python environment here to actually load up these CSV files. They're just comma separated value data files. And massage that data, clean it up a little bit, and get it into a form that Keras can accept. So We'll start by importing the pandas library. We'll call it PD for short. I've built up this array of column names because it's not actually part of the CSV file, so I need to provide that by hand. So the columns of the input data are going to be the political party, Republican or Democrat, and then a list of different votes that they voted on. So for example, we can see whether each politician voted yay or nay on religious groups in schools. I'm not really sure what the details of that particular bill were, but by reading these, you can probably guess the direction that the different parties would probably vote toward. So we'll go ahead and read that CSV file using pandas read CSV function. We will say that any missing values will be populated with a question mark, and we'll pass in a names array of the feature names so we know what to call the columns. Then we'll just display the resulting data frame using the head command. So go ahead and hit Shift Enter to get that up. And we should see something like this. It's just the first 5 entries. So for the first 5 politicians at the head of our data, we can see how each person's party is in the label that we've assigned to that person, the known label that we're going to try to predict, and their votes on each issue. Now we can also use the describe function on the resulting data frame to get a high-level overview of the nature of the data. For example, you can see there's a lot of missing data. For example, even though that there's 435 people that have a party associated with them, only 387 of them actually had a vote on the water project cost sharing bill, for example. So we have to deal with missing data here somehow. And the easiest thing to do is to just throw away rows that have missing data. Now, in the real world, you'd want to make sure that you're not introducing some sort of unintentional bias by doing that. You know, maybe there is more of a tendency for Republicans to not vote than Democrats or vice versa. If that were the case, then you might be biasing your analysis by throwing out politicians that didn't vote on every actual issue here. But let's assume that there is no such bias, and we can just go ahead and drop those missing values. That's what this little line here does. It says drop NA in place equals true. That just means that we're going to drop any rows that are missing data from our voting data frame, and then we'll describe it again. And we should see that every column has the same count because there is no missing data at this point. So we've winnowed things down to 232 politicians here. Not ideal, but hey, that's what we have to work with. Next thing we need to do is actually massage this data into a form that Keras can consume. So Keras does not deal with y's and n's, it deals with numbers. So let's replace all the y's and n's with ones and zeros using this line here. Pandas has a handy-dandy replace function on data frames you can use to do that. And similarly, we'll replace the strings Democrat and Republican also with the numbers 1 and 0. So this is turning this into a binary classification problem. If we classify someone as belonging to label 1, that will indicate they're a Democrat, and label 0 will indicate that they're a Republican. So let's go ahead and run that to clean up that data. And we should see now, if we run ahead on that data frame again, everything has been converted to numerical data between 0 and 1, which is exactly what we want for the input to a neural network. All right, finally, let's extract this data into NumPy arrays that we can actually feed to Keras. So to do that, we're just going to call .values on the columns that we care about. We're going to extract all of the feature columns into the features array and all of the actual labels, the actual parties, into an all classes array. So let's go ahead and hit enter to get that in. And at this point, I'm going to turn it over to you for now. The code snippets you need were actually covered in the slides just prior to coming out to this notebook here, so just refer back to that, and that should give you the stuff you need to work off of and actually give things a go here. So I want you to try it yourself. Now, my answer is below here, no peeking. I put a little image there to try to stop you from scrolling further than you should. But if you want to hit pause here, we can come back later and you can compare your results to mine. Okay, so at this point, I want you to pause this video and give it a go yourself. And when you think you've got something up and running, or if you just want to skip ahead and see how I did it, hit play again and I'll show you right now. All right, I hope you did your homework here. Let's go ahead and take a look at my implementation here. Again, it's pretty much straight up taken from the slides that I showed you earlier. All we're going to do is import the stuff we need from Keras here. We're using dense, dropout, and sequential. And we're also going to use cross-val score to actually evaluate our model and actually illustrate integrating Keras with scikit-learn like we talked about as well. So when we're integrating with scikit-learn, we need to create a function that creates our model so we can pass that into cross-val score ultimately. We're going to create a sequential model, and we're just going to follow the pattern that we showed earlier of doing a binary classification problem. So in this case, we have 17 input features, the 17 issues that people voted on. We are going to use a ReLU activation function with a layer of 32 neurons, And a pretty common pattern is to start with a large number of neurons in one layer and winnow things down as you get to higher layers. So we're going to distill those 32 neurons down to another hidden layer of 16 neurons. And I'm using the term units in this particular example here. A little bit of an aside. More and more researchers are using the term unit instead of neuron, and you're seeing that in some of the APIs and libraries that are coming out. Reason being is that we're starting to diverge a little bit between artificial neural networks and how they work and how the human brain actually works. In some cases, we're actually improving on biology. So some researchers are taking issue with actually calling these artificial neurons because we're kind of moving beyond neurons and they're kind of becoming their own thing at this point. Finally, we'll have one last layer with a single output neuron for our binary classification with a sigmoid activation function to choose between 0 and 1. And we will use the binary cross entropy loss function, RMS prop optimizer, and kick it off. At that point, we can set up a Keras classifier to actually execute that, and we will create an estimator object from that we can then pass into scikit-learn's cross-val score to actually perform k-fold cross-validation automatically, and we will display the mean result when we're done. So, Shift-Enter, and let's see how long this takes. Mind you, in 1984, politicians were not as polarized as they are today, so it might be a little bit harder than it would be today to actually predict someone's parties just based on their votes. It would be very interesting to see if that's the case using more modern data. Hey, we're done already. 93.9% accuracy, and that's without even trying too hard. So, we didn't really spend any time tuning the topology of this network at all. Maybe you could do a better job. If you did get a significantly better results, post that in the course here. I'm sure other students would like to hear about what you did. So there you have it, using Keras for a more interesting example, predicting people's political parties using a neural network, and also integrating it with scikit-learn to make life even easier. That's the magic of Keras for you. So far we've seen the power of just using a simple multi-layer perceptron to solve a wide variety of problems. But you can take things up a notch. You can arrange more complicated neural networks together and do more complicated problems with them. So let's start by talking about convolutional neural networks, or CNNs for short. Usually you hear about CNNs in the context of image analysis, and their whole point is to find things in your data that might not be exactly where you expect it to be. So technically we call this feature location invariant. That means that if you're looking for some pattern or some feature in your data, but you don't know where exactly it might be in your data, a CNN can scan your data and find those patterns for you wherever they might be. So for example, in this picture here, that stop sign could be anywhere in the image, and a CNN is able to find that stop sign no matter where it might be. Now, it's not just limited to image analysis. It can also be used for any sort of problem where you don't know where the features you are might be located within your data. And machine translation or natural language processing tasks come to mind for that. You don't necessarily know where the noun or the verb or phrase that you care about might be in some paragraph or sentence that you're analyzing, but a CNN can find it and pick it out for you. Sentiment analysis is another application of CNNs. You might not know exactly where a phrase might be that indicates some happy sentiment or some frustrated sentiment or whatever you might be looking for, but a CNN can scan your data and pluck it out. And you'll see that the idea behind it isn't really as complicated as it sounds. This is another example of using fancy words to make things sound more complicated than they really are. So how do they work? Well, CNNs, convolutional neural networks, are inspired by the biology of your visual cortex. It takes cues from how your brain actually processes images from your retina, and it's pretty cool. And it's also another example of interesting emergent behavior. So the way your eyes work is that individual groups of neurons service a specific part of your field of vision. So we call these local receptive fields. They are just groups of neurons that respond only to a part of what your eyes see. It subsamples the image coming in from your retinas and just has specialized groups of neurons for processing specific parts of the field of view that you see with your eyes. Now these little areas overlap each other to cover your entire visual field, and this is called convolution. Convolution is just a fancy word of saying I'm going to break up this data into little chunks and process those chunks individually. And then they'll assemble a bigger picture of what you're seeing higher up in the chain. So the way it works within your brain is that you have many layers. It is a deep neural network that identifies various complexities of features, if you will. So the first layer that you go into from your convolutional neural network inside your head might just identify horizontal lines or lines at different angles or, specific kinds of edges. We call these filters. And that might feed into a layer above them that would then assemble those lines that it identified at the lower level into shapes. And maybe there's a layer above that that would be able to recognize objects based on the patterns of shapes that you see. And then if you're dealing with color images, we have to multiply everything by 3 because you actually have specialized cells within your retina for detecting red, green, and blue light. And we need to assemble those together as well. Those each get processed individually too. So that's all a CNN is. It is just taking a source image or source data of any sort really, breaking it up into little chunks called convolutions, and then we assemble those and look for patterns at increasingly higher complexities at higher levels in your neural network. So how does your brain know that you're looking at a stop sign there? Let's talk about this in more colloquial language, if you will. So like we said, you have individual local receptive fields that are responsible for processing specific parts of what you see. And those local receptive fields are scanning your image and they overlap with each other, looking for edges. You might notice that your brain is very sensitive to contrast and edges that it sees in the world. Those tend to catch your attention, right? That's why the letters on this slide catch your attention, because there's high contrast between the letters and the white background behind them. So at a very low level, you're picking up the edges of that stop sign and the edges of the letters on the stop sign. Now a higher level might take those edges and recognize the shape of that stop sign. It says, oh, there's an octagon there. That means something special to me. Or those letters form the word stop. That means something special to me too. And ultimately that will get matched against whatever classification pattern your brain has of a stop sign. So no matter which receptive field picked up that stop sign, at some layer it will be recognized as a stop sign. And furthermore, because you're processing data in color, it can also use the information that this stop sign is red and further use that to aid in its classification of what this object really is. So somewhere in your head there's a neural network that says, hey, if I see edges arranged in an octagon pattern that has a lot of red in it and says stop in the middle, that means I should probably hit the brakes on my car. And at some even higher level, where your brain is actually doing higher reasoning, that's what happened. There's a wire that says, hey, there's a stop sign coming up here, I better hit the brakes in my car. And if you've been driving long enough, you don't even really think about it anymore, do you? Like it's almost hardwired, and that literally may be the case. Anyway, a convolutional neural network, an artificial convolutional neural network, works the same way, same exact idea. So how do you build a CNN with Keras? Obviously, you probably don't want to do this at the low-level TensorFlow layer. You can, but CNNs get pretty complicated. So a higher-level library like Keras becomes essential. First of all, you need to make sure your source data is of the appropriate dimensions, of the appropriate shape, if you will. And you are going to be preserving the actual 2D structure of an image if you're dealing with image data here. So the shape of your data might be the width times the length times the number of color channels. And by color channels, I mean if it's a black and white image, there's only one color, black and white. So you'd only have one color channel for a grayscale image. But if it's a color image, you'd have 3 color channels, one for red, one for green, and one for blue, because you can create any color by combining red, green, and blue together. Okay. Now, there are some specialized types of layers in Keras that you use when you're dealing with convolutional neural networks. For example, there's the conv2D layer type that does the actual convolution on a 2D image. And again, convolution is just breaking up that image into little subfields that overlap each other for individual processing. There's also a conv1D and a conv3D layer available as well. You don't have to use CNNs with images. Like we said, it can also be used with text data, for example. That might be an example of one-dimensional data. And there's also a conv3D layer is available as well if you're dealing with 3D volumetric data of some sort. So a lot of possibilities there. Another specialized layer in Keras for CNNs is max pooling 2D. Obviously, there's a 1D and 3D variant of that as well. The idea of that is just to reduce the size of your data down. So if I take just the maximum value seen in a given block of an image and reduce the 2-layer down to those maximum values, it's just a way of shrinking the images in such a way that it can reduce the processing load on the CNN. As you'll see, processing CNNs is very computing intensive, and the more you can do to reduce the work you have to do, the better. So if you have more data in your image than you need, a max pooling 2D layer can be useful for distilling that down to the bare essence of what you need to analyze. Finally, at some point, you need to feed this data into a flat layer of neurons, right? At some point, it's just going to go into a perceptron. And at this stage, we need to flatten that 2D layer into a 1D layer so we can just pass it into a layer of neurons. And from that point, it just looks like any other multi-level perceptron. So the magic of CNNs really happens at a lower level. Ultimately, it gets converted into what looks like the same types of multi-layer perceptrons that we've been using before. The magic happens in actually processing your data, convolving it, and reducing it down to something that's manageable. So typical usage of image processing with a CNN would look like this. You might start with a conv2D layer that does the actual convolution of your image data. You might follow that up with a max pooling 2D layer on top of that. That distills that image down, just shrinks the amount of data that you have to deal with. You might then do a dropout layer on top of that, which just prevents overfitting like we talked about before. And at that point, you might apply a flatten layer to actually be able to feed that data into a perceptron. And that's where a dense layer might come into play. So a dense layer in Keras is just a perceptron, really. It's a layer of a hidden layer of neurons. From there, you might do another dropout pass to further prevent overfitting, and finally do a softmax to choose the final classification that comes out of your neural network. Now, like I said, CNNs are compute intensive. They are very heavy on your CPU, your GPU, and your memory requirements. Shuffling all that data around and convolving it adds up really, really fast. And beyond that, there's a lot of what we call hyperparameters, a lot of different knobs and dials that you can adjust on CNNs. So in addition to the usual stuff you can tune, like the topology of your neural network, or what optimizer you use, or what loss function you use, or what activation function you use, there's also choices to make about the kernel sizes. What is the area that you actually convolve across? How many layers do you have? How many units do you have? How much pooling do you do when you're reducing the image down? There's a lot of variance here. There's almost an infinite amount of possibilities here for configuring a CNN. And often just obtaining the data to train your CNN with is the hardest part. So for example, if you own a Tesla, that's actually taking pictures of the world around you and the road around you and all the street signs and traffic lights as you drive. And every night it sends all those images back to some data server somewhere so Tesla can actually run training on its own neural networks based on that data. So if you slam on the brakes while you're driving a Tesla, at night that information is going to be fed into a big data center somewhere, and Tesla's going to crunch on that and say, hey, is there a pattern here to be learned of what I saw from the cameras from the car that means you should slam on the brakes in the case of a self-driving car? And if you think about the scope of that problem, just the sheer magnitude of processing and obtaining and analyzing all of that data, that becomes very challenging in and of itself. Now, fortunately, the problem of tuning the parameters doesn't have to be as hard as I described it to be. There are specialized architectures of convolutional neural networks that do some of that work for you. So a lot of research goes into trying to find the optimal topologies and parameters for a CNN for a given type of problem. And you can just think of this as like a library you can draw from. So, for example, there's the Linnet 5 architecture that you can use that's suitable for handwriting recognition in particular. There's also one called AlexNet, which is appropriate for image classification. It's a deeper neural network than Linnet. So in the example we talked about on the previous slides, we only had a single hidden layer, but you can have as many as you want, really. It's just a matter of how much computational power you have available. There's also something called Google Linnet. You can probably guess who came up with that. It's even deeper, but it has better performance because it introduces this concept called inception modules. They basically group convolution layers together, and that's a useful optimization for how it all works. Finally, the most sophisticated one today is called ResNet. That stands for residual network. It's an even deeper neural network, but it maintains performance by what's called skip connections. So it has special connections between the layers of the perceptron to further accelerate things. So it sort of like builds upon the fundamental architecture of a neural network to optimize its performance. And as you'll see, CNNs can be very demanding on performance. So with that, let's give it a shot. Let's actually use a CNN and see if we can do a better job at image classification than we've done before using one. All right, so let's actually run a convolutional neural network using Keras. In your course materials, you should see a Keras-CNN Python notebook. Go ahead and open that up. And we're going to revisit the MNIST handwriting recognition problem, where we try to classify a bunch of images of people drawing the numbers 0 through 9 and see if we can do a better job of it using CNNs. Again, CNNs are better suited to image data in general, especially if you don't know exactly where the feature you're looking for is within your image. So we should expect to get better results here. All right, so we're going to start by importing all the stuff we need from Keras. We're going to import the MNIST dataset that we're playing with, the sequential model so we can assemble our neural network, and then we're going to import all these different layer types that we talked about in the slides, the dense, dropout, conv 2D, max pooling 2D, and flatten layer types. And in this example, we'll use the RMS prop optimizer. Go ahead and kick that off. And the rest here for loading up the training and test data is going to look just like it did before. Still waiting for that Keras to initialize itself there. All right, so that should load up the MNIST dataset. We're going to shape this data a little bit differently. So since convolutional neural networks can process 2D data in all their 2D glory, we're not going to reshape that data into flat 1D arrays of 768 pixels. Instead, we're going to shape it into the width times the length times the number of color channels. So in this case, our data is grayscale in nature, so there's only a single color channel that just defines how white or dark the image is, the specific pixel is. And there's a couple of different ways that data can be stored. So we need to handle a couple of different cases here. It might be organized as color channels by width times length, or it might be width times length times color channels. So this is what this little bit of code here is dealing with. But either way, we will see if it's a channels first format or not and reshape the data accordingly. And we're going to store that shape in this thing called input shape. So that's the shape of our input test data and train data for that matter. As before, we're going to scale this data down so it comes in as 8-bit byte data, and we need to convert that into normalized floating point data instead. So we'll convert that data to floating point 32-bit values and then divide each pixel by 255 to transform that into some number between 0 and 1. Go ahead and hit Shift Enter in there to kick that off. All right, and as before, we will convert the label data into one-hot categorical format because that will match up nicely with the output of our neural network. And nothing different here. We're just going to, again, do a sanity check to make sure that we successfully imported our data. So we'll pick a random training set sample to print out here and display. And there's the one-hot format of the 3 label, 0, 1, 2, 3. That's correct. Human readable format 3, and it looks like that. Sure enough, that looks like the number 3. So it looks like our data is in good shape for processing. So now let's actually set up a CNN and see how that works. So let's walk through what's going on in this next code block here. As before, we start off by setting up a sequential model that just allows us to very easily build up layers to build up our neural network here. And we will start with a conv2D layer. So what this syntax here means is that our convolutional 2D layer is going to have 32 windows, or 32 regional fields, if you will, that it will use to sample that image with. And each one of those samples will be of a 3x3 kernel size. It also needs to know the shape of your input data, which we stored previously. That's the 1 by 28 by 28 or 28 by 28 by 1, depending on the input format there. We will then add a second convolutional filter on top of that to hopefully identify higher level features. This one will have 64 kernels, also of 3 by 3 size, and we are going to use a ReLU activation function on that as well. So we've built up 2 convolution layers here. And again, you want to just reuse any previous research you can do for a given problem. There are so many ways to configure CNNs that if you start from scratch, you're going to have a very hard time to tune it, especially when you consider how long it takes to iterate between each run. These are very resource intensive. So I've just taken this from the CNN example that comes with the Keras library and drawn my initial topology from it. So now that we've done our convolution layers, we're going to do a max pooling 2D step to actually reduce that down a little bit. So we're going to take a 2x2 pool size, and for each 2x2 pixel block at this stage, we're going to reduce that down to a single pixel that represents the maximum pixel found within that pool. So note that the pool size can be different from the underlying kernel size from the convolution you did. So really this is just a technique for shrinking your data down to something that's more manageable. At this point, we'll do a dropout pass to prevent overfitting. We will then flatten what we have so far, so that will take our 2D data and flatten it to a 1D layer. And from this point, it's just going to look like any other multi-layer perceptron, just like we used before. So all the magic of CNNs has happened at this point, and now we're just going to convert it down to a flat layer that we input into a hidden layer of neurons. In this case, we're going to have 128 in that layer. Again, with a ReLU activation function, we'll do one more dropout pass to prevent overfitting, and finally choose our final categorization of the numbers 0 through 9 by building one final output layer of 10 neurons with the Softmax activation function on it. All right, so let's go ahead and let that run. Again, nothing's really happening until we actually kick off the model, so that doesn't take any time at all. We can do a model.summary just to double check that everything is the way that we intended it to be. And you can see that we have our 2 convolution layers here, followed by a pooling layer, followed by a dropout, a flatten, and from there we have a dense dropout and dense multi-layer perceptron to actually do our final classification. All right. Finally, we need to compile that model with a specific optimizer and loss function. In this case, we're going to use the Atom optimizer and categorical cross entropy because that's the appropriate loss function for a multiple category classification problem. And finally, we will actually run it. Now, Like I said, CNNs are very expensive to run. So let me talk about what this command does first of all. Nothing unusual here. It just says that we're going to run batches of 32, which is smaller than before because there is a much higher computational cost to this. We're only going to run 10 epochs this time because, again, it takes a long time. More would be better, but there's only so much we have time to do. Verbosity level 2 because that's what you want to choose for running within an IPython notebook, and we will pass in our validation test data for it to work with as well. Now, I am not going to actually run this because this could actually take about an hour to run. And if you don't have a beefy machine, it might not finish at all. You know, if you don't have enough RAM or enough CPU power, this might even be too much for one system. So I'm going to skip ahead here. I actually ran this earlier, and it did take about 45 minutes. But you can see that it very quickly converged to a very good accuracy value here, and it was still increasing. So there probably would have been value to going even beyond 10 iterations of the training here. But even after just 10 epochs or 10 iterations, we ended up with an accuracy of over 99%. And we can actually evaluate that based on our test data and recreate that 99% accuracy. So that's kind of awesome. So CNNs, definitely worth doing if accuracy is key. And for applications where lives are at stake, such as a self-driving car, obviously that's worth the effort, right? You want complete accuracy of detecting if there's a stop sign in front of you, ideally, right? Even 0.1% error is going to be unacceptable in a situation like that. So that's the power of CNNs. They are more complicated. They take a lot more time to run. But as we said, the power of TensorFlow, which Keras is running on top of, means that you can distribute this work across an entire cloud of computers and an entire array of GPUs that are on each computer. So there are ways of accelerating this. We're just not taking advantage of that in this little example here. It's just illustrative. So there you have it, your first convolutional neural network, and you can see how powerful it is in successfully doing image classification, among other things. So cool, let's move on to another type of neural network next. Let's talk about another kind of neural network, the recurrent neural network. What are RNNs for? Well, a couple of things. Basically, they're for sequences of data, and that might be a sequence in time. So you might use it for processing time series data, where you're trying to look at a sequence of data points over time and predict the future behavior of something over time in turn. So RNNs are based for sequential data of some sort. And some examples of time series data might be weblogs, where you're receiving different hits to your website over time, or sensor logs, where you're getting different inputs from sensors from the Internet of Things. Or maybe you're trying to predict stock behavior by looking at historical stock trading information. These are all potential applications for recurrent neural networks because they can take a look at the behavior over time and try to take that behavior into account when it makes future projections. Another example might be if you're trying to develop a self-driving car. You might have a history of where your car has been, its past trajectories, and maybe that can inform how your car might want to turn in the future. So you might take into account the fact that your car has been turning along a curve to predict that perhaps it should continue to drive along a curve until the road straightens out. And another example, it doesn't have to just be time. It can be any kind of sequence of arbitrary length. So something else that comes to mind are languages, sentences. They're just sequences of words, right? So you can also apply RNNs to language or machine translation or producing captions for videos or images. These are examples of where the order of words in a sentence might matter, and the structure of the sentence and how these words are put together could convey more meaning than you could get by just looking at those words individually without context. So again, an RNN can make use of that ordering of the words and try to use that as part of its model. Another interesting application of RNNs is machine-generated music. You can also think of music sort of like text, where instead of a sequence of words or letters, you have a sequence of musical notes. So it's kind of interesting. You can actually build a neural network that can take an existing piece of music and sort of extend upon it by using a recurrent neural network to try to learn the patterns that were aesthetically pleasing to the music in the past. Conceptually, this is what a single recurrent neuron looks like in terms of a model. So it looks a lot like an artificial neuron that we've looked at before. The big difference is this little loop here, okay? So now, as we run a training step on this neuron, some training data gets fed into it, or maybe this is an input from a previous layer in our neural network, and it will apply some sort of step function after summing all the inputs into it. In this case, we're going to be drawing something more like a hyperbolic tangent because mathematically we want to make sure that we preserve some of the information coming in more of a smooth manner. Now, usually we would just output the result of that summation and that activation function as the output of this neuron, but we're also going to feed that back into the same neuron. So the next time we run some data through this neuron, that data from the previous run also gets summed in to the results. Okay, so as we keep running this thing over and over again, we'll have some new data coming in that gets blended together with the output from the previous run through this neuron, and that just keeps happening over and over and over again. So you can see that over time, the past behavior of this neuron influences its future behavior, and it influences how it learns. Another way of thinking about this is by unrolling it in time. So what this diagram shows is the same single neuron, just at 3 different time steps. And when you start to dig into the mathematics of how RNNs work, this is a more useful way of thinking about it. So if we consider this to be time step 0, you can see there's some sort of data input coming into this recurrent neuron, and that will produce some sort of output after going through its activation function. And that output also gets fed into the next time step. So if this is time step 1 with this same neuron, you can see that this neuron is receiving not only a new input, but also the output from the previous time step. And those get summed together, the activation function gets applied to it, and that gets output as well. And the output of that combination then gets fed onto the next time step, called as time step 2, where a new input for time step 2 gets fed into this neuron, and the output from the previous step also gets fed in. They get summed together, the activation function is run, and we have a new output. This is called a memory cell because it does maintain memory of its previous outputs over time. And you can see that even though it's getting summed together at each time step, over time, those earlier behaviors kind of get diluted, right? So, we're adding in that time step to that time step, and then the sum of those two things end up working into this one. So one property of memory cells is that more recent behavior tends to have more of an influence on the current behavior that you get out of a recurrent neuron. And this can be a problem in some applications. So there are ways to work against that we can talk about later. Stepping this up, you can have a layer of recurrent neurons, so you don't have to have just one, obviously. So in this diagram, we are looking at 4 individual recurrent neurons that are working together as part of a layer. And you can have some input going into this layer as a whole. That gets fed into these 4 different recurrent neurons, and then the output of those neurons can then get fed back to the next step to every neuron in that layer. So all we're doing is scaling this out horizontally. So instead of a single recurrent neuron, we have a layer of 4 recurrent neurons in this example, where all of the output of those neurons is feeding in to the behavior of those neurons in the next learning step. Okay, so you can scale this out to have more than one neuron and learn more complicated patterns as a result. RNNs open up a wide range of possibilities because now we have the ability to deal not just with vectors of information, static snapshots of some sort of a state, we can also deal with sequences of data as well. So there are 4 different combinations here that you can deal with. We can deal with sequence-to-sequence neural networks. If we have the input is a time series or some sort of sequence of data, we can also have an output that is a time series or some sequence of data as well. So if you're trying to predict stock prices in the future based on historical trades, that might be an example of sequence-to-sequence topology. We can also mix and match sequences with the older vector static states that we predicted back with just using multi-layer perceptrons. We would call that a sequence to vector. So if we were starting with a sequence of data, we could produce just a snapshot of some state as a result of analyzing that sequence. An example might be looking at the sequence of words in a sentence to produce some idea of the sentiment that that sentence conveys. And we'll actually look at that in an example shortly. You can go the other way around too. You can go from a vector to a sequence. So an example of that would be taking an image, which is a static vector of information, and then producing a sequence from that vector, for example, words in a sentence, creating a caption from an image. And we can chain these things together in interesting ways as well. We can have encoders and decoders built up that feed into each other. For example, we might start with a sequence of information from a sentence of some language, embody what that sentence means as some sort of a vector representation, and then turn that around into a new sequence of words in some other language. So that might be how a machine translation system could work, for example. You might start with a sequence of words in French, build up a vector that sort of embodies the meaning of that sentence, and then produce a new sequence of words in English or whatever language you want. That's an example of using a recurrent neural network for machine translation. So lots of exciting possibilities here. Training RNNs, just like CNNs, is hard. In some ways, it's even harder. The main twist here is that we need to backpropagate not only through the neural network itself and all of its layers, but also through time. And at a practical standpoint, every one of those time steps ends up looking like another layer in our neural network while we're trying to train our neural network. And those time steps can add up fast. So over time, we end up with like an even deeper and deeper neural network that we need to train. And the cost of actually performing gradient descent on that increasingly deep neural network becomes increasingly large. So to put an upper cap on that training time, often we limit the backpropagation to a limited number of time steps. We call this truncated backpropagation through time. So just something to keep in mind when you're training an RNN, you not only need to backpropagate through the neural network topology that you've created, you also need to backpropagate through all the time steps that you've built up to that point. Now, we talked earlier about the fact that as you're building up an RNN, the state from earlier time steps end up getting diluted over time because we just keep feeding in behavior from the previous step in our run to the current step. And this can be a problem if you have a system where older behavior does not matter less than newer behavior. For example, if you're looking at words in a sentence, the words at the beginning of a sentence might even be more important than words toward the end. So if you're trying to learn the meaning of a sentence, the position of the word in the sentence, there is no inherent relationship between where that word is and how important it might be in many cases. So that's an example of where you might want to do something to counteract that effect. And one way to do that is something called the LSTM cell. It stands for Long Short-Term Memory Cell. And the idea here is that it maintains separate ideas of both short-term and long-term states. And it does this in a fairly complex way. Now, fortunately, you don't really need to understand the nitty-gritty details of how it works. There is an image of it here for you to look at if you're curious. But the libraries that you use will implement this for you. The important thing to understand is that if you're dealing with a sequence of data where you don't want to give preferential treatment to more recent data, you probably want to use an LSTM cell instead of just using a straight-up RNN. There's also an optimization on top of LSTM cells called GRU cells. That stands for Gated Recurrent Unit. It's just a simplification on LSTM cells that performs almost as well. So if you need to strike a balance or a compromise between performance in the terms of how well your model works and performance in the terms of how long it takes to train it, a GRU cell might be a good choice. Training them is really hard. If you thought CNNs was hard, wait till you see RNNs. They are very sensitive to the topologies that you choose and the choice of hyperparameters. And since we have to simulate things over time and not just through, the static topology of your network, they can become extremely resource intensive. And if you make the wrong choices here, you might have a recurrent neural network that doesn't converge at all. It might be completely useless even after you've run it for hours to see if it actually works. So again, it's important to work upon previous research to try to find some sets of topologies and parameters that work well for similar problems to what you're trying to do. This all makes a lot more sense with an example, and you'll see that it's really nowhere near as hard as it sounds when you're using Keras. Now, I used to work at IMDB, so I can't resist using a movie-related example, so let's dive into that next and see RNNs, recurrent neural networks, in action. So let's have some fun with recurrent neural networks. If you go into the course materials, you should see a Keras-RNN Python notebook. Go ahead and open that up. And although RNNs sounded pretty scary in the slides, using them in Keras is actually fairly straightforward. It's still tricky to tune things properly, but assuming you have some sort of a template of a similar problem to work from, it's quite easy in practice here. What we're going to do here is try to do sentiment analysis. So this is going to be an example of a sequence to vector RNN problem, where we're taking the sequence of words in a user-written movie review, and we try to output a vector that's just a single binary value of whether or not that user liked the movie or not, whether they gave it a positive rating. So this is an example of doing sentiment classification using real user review data from IMDB. And since I used to run IMDB's engineering department, this is a little bit too tempting for me not to do as an example here. Now, mind you, just to give credit where credit is due, this is drawn heavily upon one of the examples that ships with Keras, the IMDB LSTM sample. I've sort of embellished on it a little bit here, but the idea is there, just to give credit where credit's due. And it does warm my heart, by the way, that they include the IMDB dataset as part of Keras for you to experiment with. So it's bringing back good memories for me. I enjoyed working there. Anyhow, this is another example of how we're going to use LSTM cells, long short-term memory cells, because again, when you're dealing with textual data, a sequence of words in a sentence, it doesn't necessarily matter where in the sentence that word appeared. You don't want the property of words toward the end of the sentence counting more toward your classification than words at the beginning of the sentence. In fact, often it's the other way around. So we're going to use an LSTM cell to try to counteract that effect that you see in normal RNNs where data becomes diluted over time. or as the sequence progresses in this example. So let's just dive in and see how it works. We'll start by importing all the stuff that we need from Keras. We're going to use a sequence, pre-processing module, sequential model, so we can embed different layers together. We're going to introduce a new embedding layer as part of our RNN in addition to the dense layer that we had before. We will import the LSTM module. And finally, we'll import the IMDB dataset. So let's go ahead and Shift Enter to do all of that and get Keras initialized. Again, I'm assuming that you've already installed TensorFlow and Keras into Python using the pip command. Give that a few seconds to load up. And that's done now. So now we can import our training and testing data. Like I said, Keras has a handy-dandy IMDB dataset pre-installed. Oddly, it has 5,000 training reviews and 25,000 testing reviews, which seems backwards to me, but yeah, it is what it is. The one parameter you're seeing here for num words indicates how many unique words that you want to load into your training and testing dataset. So by saying num words equals 20,000, that means that I'm going to limit my data to the 20,000 most popular words in the dataset. So if someone uses some really obscure word, it's not going to show up in our input data. Let's go ahead and load that up. And since it does have to do some thinking, it doesn't come back instantly, but pretty quick. Okay, we're in business here. Let's take a peek at what this data looks like. So let's take a look at the first instance of training data here. And what the heck? It's just a bunch of numbers. It doesn't look like a movie review to me. Well, you can be very thankful to the folks at Keras for doing this for you. So the thing is, when you're doing machine learning in general, usually models don't work with words, they work with numbers, right? So we need to convert these words to numbers somehow as a first step. And Keras has done all this pre-processing for you already. So, you know, the number 1 might correspond to the word the, or I actually have no idea what it corresponds to. But they've encoded each unique word between 0 and 20,000, because we said we wanted the 20,000 most popular words, to numbers. Okay, so it's kind of a bummer that we can't actually read these reviews and get sort of an intuitive meaning of what these reviews are saying, but it saves us a whole lot of work. And I've said before that often a lot of the work in machine learning is not so much building your models and tuning them, it's just processing and massaging your input data and making sure that your input data looks good to go. So even though this doesn't look like a movie review, it is a movie review. They've just replaced all of the words with unique numbers that represent each word. We can also take a look at the training data. So the classification of this particular review was 1, which just means that they liked it. So the only classifications are 0 and 1, which correspond to a negative or a positive sentiment for that review. Okay, so we have all of our input data converted already to numerical format. That's great. Now we just have to go ahead and set things up. Let's start by creating some vectors for input here. So we're going to break out our training and test data here. We're going to call sequence.pad sequences just to make sure that everything has a limit on them to 80 words. So the reason we're doing this is because, like we said, RNNs can blow up very quickly. You have to backpropagate through time. So we want to have an upper bound on how many time steps we need to backpropagate to. So by saying max len equals 80, that means we're only going to look at the first 80 words in each review and limit our analysis to that. So that is a way of truncating our backpropagation through time. It's sort of a low-tech way of doing it, but it's effective. Otherwise, we would be running this thing for days. Okay, so the only point here is to trim all of these reviews in both the training and the test data set to their first 80 words, which again have been converted to numbers for us already. Let's build up the model itself. Hey, we didn't actually run that, so let's go ahead and hit Shift-Enter on that block. Okay. Now we can build up the model itself, and for such a complicated neural network, I think it's pretty remarkable how few lines of codes are going on here. So let's talk through this. We'll start by creating a sequential model, meaning that we can just build up the topology of our network one step at a time here. So we'll start with some additional pre-processing. We're using what's called an embedding layer here, and all that does is convert our input data of words up to the first 80 words in a given review into dense vectors of some fixed size. So it's going to create a dense vector of a fixed size of 20,000 words and then funnel that into 128 hidden neurons inside my neural network. So that's all that embedding layer is doing. It's just taking that input textual data that's been encoded and converting that into a format that's suitable for input into my neural network. Then, with a single line of code, we build our recurrent neural network. So we just say add an LSTM, and we can go through the properties here. We're going to say we're going to have 128 recurrent neurons in that LSTM layer. And we can also specify dropout terms just in that same command here. So we can say that we want to do a dropout of 20%. And that's all there is to it. That one line of code sets up our LSTM neural network with 128 recurrent neurons and adds dropout phases of 20% all in one step. Finally, we need to boil that down to a single output neuron with a sigmoid activation function because we're dealing with a binary classification problem, and that's it. So we've defined the topology of our network with just 4 lines of code, even though it's a very complicated recurrent neural network using LSTM cells and dropout phases, but Keras makes that all very easy to do. We then need to tell Keras how to optimize this neural network and how to train it. So we will use binary cross entropy because this is ultimately a binary classification problem. Did the person like this movie or not? We'll use the atom optimizer this time, just because that's sort of the best of both worlds for optimizers. And then we can kick it off. So let's go ahead and run these 2 previous blocks. Shift Enter. Shift Enter. And at this point, you're ready to actually train your neural network. And let's just walk through what's going on here. It's very similar from the previous examples. In this case, we're going to use batch sizes of 32 reviews at once. We're going to run it over 15 training steps, or epochs, set a verbosity layer that's compatible with IPython notebooks, and provide the validation data for its use as well. Now, again, I'm not going to actually run this right now because it will take about an hour. Like I said, RNNs are hard. They take a lot of computing resources. And since all I'm doing is running this on my single CPU, I don't even have things configured to use my GPU or let alone a cluster of computers, this takes a long time. But I did run it earlier, and you can see the results here. So over 15 epochs, you can see that the accuracy that it was measuring on the training data was beginning to converge. Seems like after about 13 steps, it was getting about as good as it was going to get. And then furthermore, we can actually evaluate that model given the testing data set. So let's go ahead and call evaluate on that with our test data, again using 32 batches. And if we were to run that, we would see that we end up with an accuracy of 81% on our model here. Doesn't sound that impressive, but when you consider that all we're doing is looking at the first 80 words of each review and trying to figure out, just based on that beginning, whether or not a user liked the movie or not, that's not too bad. But again, step back and think about what we just made here. We've made a neural network that can essentially read English language reviews and determine some sort of meaning behind them. In this case, we've trained it how to take a sequence of words at the beginning of a movie review that some human wrote and classify that as a positive review or a negative review. So in a very real sense, we've at some level, at a very basic level, taught our computer how to read. How cool is that? And the amount of code that we wrote to do that was minimal, right? So it's kind of mind-blowing. It's really just a matter of knowing what technique to use to build your neural network, providing the appropriate training data, and then your neural network does the rest. It's really kind of spooky when you sit back and think about it. Anyway, cool stuff. So it's a great example of how powerful Keras can be, and a great example of an application of a recurrent neural network, not using the typical example of stock trading data or something like that, but instead for sentiment analysis, where we took a sequence of words and used that to create a binary classification of a sentiment based on that sequence. So fun stuff, RNNs and Keras. A lot of people are talking about the ethics of deep learning. Are we actually creating something that's good for humanity or ultimately bad for humanity? So let's go there. Now, I'm not going to preach to you about sentient robots taking over the world. I mean, maybe that will be a problem 50 years from now, maybe even sooner, but for the immediate future, it's more subtle ways in which deep learning can be misused that you should concern yourself with. And as someone entering the field, either as a researcher or a practitioner, it is up to you to make sure that this powerful technology is used for good and not for evil. And sometimes this can be very subtle. So you might deploy a new technology in your enthusiasm, and it might have unintended consequences. And that's mainly what I want to talk about in this lecture, understanding unintended consequences of the systems you're developing with deep learning. First of all, it's important to understand that accuracy doesn't tell the whole story. So we've evaluated our neural networks by their ability to accurately classify something. And if we see like a 99.9% accuracy value, we congratulate ourselves and pat ourselves on the back. But often that's not enough to think about. First of all, there are different kinds of errors. There's what we call a type 1 error, which is a false positive. That's when you say that something is something that it isn't. For example, maybe you misinterpreted a tumor that was measured by some biopsy that was taken from a breast sample as being malignant. And that false positive of a malignant cancerous result could result in real unnecessary surgery to somebody. Or maybe you're developing a self-driving car, and your camera on the front of your car sees a shadow from an overpass in front of you. This has actually happened to me, by the way, and slams on the brakes because it thinks that the road is just falling away into oblivion, into this dark mass, and there's nothing for you to drive on in front of you. Both of those are not very good outcomes. They could be worse, mind you. I mean, arguably it's worse to leave a cancer untreated than to have a false positive or one, or it might be worse to actually drive off the edge of a cliff than to slam on your brakes, but these could also be very bad as well, right? You need to think about the ramifications of what happens when your model gets something wrong. Now, for the example of the self-driving car, maybe it could take the confidence level of what it thinks is in front of you and maybe work that into who's behind you. So at least if you do slam on the brakes for no reason, you can make sure there's not someone riding on your tail who's going to rear end you or something like that. So think through what happens when your model is incorrect, because even a 99.9% accuracy means that 1 times out of 1,000, you're going to get it wrong. And if people are using your system more than 1,000 times, there's going to be some bad consequence that happens as a result. You need to wrap your head around what that result is and how you want to deal with it. The second type is a false negative. And for example, you might have breast cancer but fail to detect it. You may have misclassified it as being benign instead of malignant. Somebody dies if you get that wrong, okay? So think very closely about how your system is going to be used and the caveats that you put in place and the fail-safes and the backups that you have to make sure that if you have a system that is known to produce errors under some conditions, you are dealing with those in a responsible way. Another example of a false negative would be thinking that there's nothing in front of you in your self-driving car when in fact there is. Maybe it doesn't detect the car that stopped at a stoplight in front of you. This has also happened to me. What happens then? If the driver is not alert, you crash into the car in front of you, and that's really bad. Again, people can die, okay? So people are very eager to apply deep learning to different situations in the real world, but often the real-world consequences of getting something wrong is a life and death matter, quite literally. So you need to really think about how your system is being used and make sure that your superiors and the people who are actually rolling this out to the world understand the consequences of what happens when things go wrong and the real odds of things going wrong. You know, you can't oversell your systems as being totally reliable, because I promise you they're not. There can also be hidden biases in your system. So just because the artificial neural network you've built is not human does not mean that it's inherently fair and unbiased. Remember, your model is only as good as the data that you train it with. So let's take an example. If you're going to build a neural network that can try to predict whether somebody gets hired or not just based on attributes of that person. Now, your model itself may be all pure and whatnot, but if you're feeding it training data from real humans that made hiring decisions, that training data is going to reflect all of their implicit biases. This is just one example. So you might end up with a system that is in fact racist or ageist or sexist, simply because the training data you provide it was made by people who have these implicit biases, who may not have even been fully aware of them at the time. Okay, so you need to watch out for these things. Simple things you can do. I mean, obviously, making an actual feature for this model that includes age or sex or race or religion would be a pretty bad idea, right? But I can see some people doing that. Think twice before you do something like that. But even if you don't implicitly put in features that you don't want to consider as part of your model, there might be unintended consequences or dependencies in your features that you might not have thought about. For example, if you're feeding in years of experience to the system that predicts whether or not somebody should get a job interview, you're going to have an implicit bias in there, right? The years of experience will very definitely be correlated with the age of the applicant. So if your past training data had a bias toward, white men in their 20s who are fresh out of college, your system is going to penalize more experienced candidates who might in fact be better candidates who got passed over simply because they were viewed as being too old by human people. So think deeply about whether the system you're developing has hidden biases and what you can do to at least be transparent about what those biases are. Another thing to consider is the system you just built really better than a human? So if you're building a deep learning system that the people in your sales department or your management or your investors really want to sell as something that can replace jobs and save people, or save companies money rather, you need to think about whether the system you're selling really is as good as a human, and if it's not, what are the consequences of that? For example, you can build deep learning systems that perform medical diagnoses, and you might have a very eager sales rep who wants to sell that as being better than a human doctor. Is it really? What happens when your system goes wrong? Do people die? That would be bad. It would be better to be insistent with your superiors that this system is only marketed as an supplementary tool to aid doctors in making a decision and not as a replacement for human beings making a decision that can affect life or death. Again, self-driving car is another example where if you get it wrong, if your self-driving car isn't actually better than a human being and someone puts your car on autopilot, it can actually kill people. So I see this happening already, where self-driving cars are being oversold. And there are a lot of edge cases in the world still where self-driving cars just can't cut it, where a human could. And I think that's very dangerous. Also think about unintended applications of your research. So let me tell you a story, because this has actually happened to me more than once. Sometimes you develop something that you think is a good thing that will be used for positive use in the real world, but it ends up getting twisted by other people into something that is destructive. And that's something else you need to think about. So let me tell you a story. So you need to think about how the technology you're developing might be used in ways that you never anticipated. And can those usages be, in fact, malicious? This has actually happened to me a couple of times. I'm not talking theoretically here. And this isn't just limited to deep learning. It's really an issue with machine learning in general, or really any new powerful technology. Sometimes our technology gets ahead of ourselves as a species, socially. Let me tell you one story. So this isn't actually related to deep learning, but one of the first things I built in my career was actually a military flight simulator and training simulator. Its idea was to simulate combat in sort of a virtual reality environment in order to train our soldiers to better preserve their own lives and, come out of the battlefield safely. I felt that was a positive thing. Hey, I'm saving the lives of soldiers. But after a few years, this same technology I made ended up being used in a command and control system. It was being used to help commanders actually visualize how to actually roll out real troops and actually kill real people. I wasn't okay with that, and I left the industry, in part because of that stuff. A more relevant example, back when I worked at Amazon.com, I was one of the, I don't want to take too much credit for this because the people who came up with the ideas were before me, but I was one of the early people actually implementing recommendation algorithms and personalization algorithms on the internet, taking your user behavior on the internet and distilling that down into recommendations for content to show you. And that ended up being sort of the basis that got built upon over the years that ultimately led to things like Facebook's targeting algorithms is another example of that. And, when I look at how people are using fake news and fake accounts on social media to try to spread their political beliefs or, some ulterior motive that may be financially driven and not really for the benefit of humanity, I don't feel very good about that. The technology that I created at the time just to sell more books, which seemed harmless enough, ended up getting twisted into something that really changed the course of history in ways that might be good or bad depending on your political leanings. So again, remember that if you actually have a job in deep learning and machine learning, you can go anywhere you want to. If you find yourself being asked to do something that's morally questionable, you don't have to do it. You can find a new job tomorrow, okay? This is a really hot field, and by the time you have real-world experience in it, the world's your oyster. If you find yourself being asked to be doing something that's morally questionable, you can say no. Someone else will hire you tomorrow, I promise you, if you're any good at all. So I see this happening a lot lately. There's a lot of people publishing research about using neural networks to crack people's passwords or to, illustrate how it can be used for evil, for example, by trying to predict people's sexual orientation just based on a picture of their face. This can't go anywhere good, guys. What are you trying to show by actually publishing this sort of a research? So think twice before you publish stuff like that. Think twice before you implement stuff like that for an employer, because your employer only cares about making money, about making a profit. They are less concerned about the moral implications, about the technology you're developing to deliver that profit. And people will see what you're building out there, and they will probably take that same technology, those same ideas, and twist it into something you may not have considered. So I just want you to keep these ideas and these concerns in the back of your head, because you are dealing with new and powerful technologies here. And it's really up to us as technologists to try to steer that technology in the right direction and use it for the good of humanity and not for the detriment of humanity. Sounds very, very high level, high horse preachy, I know, but these are very real concerns. And there are, a lot of people out there that share my concerns. So please consider these concerns as you delve into your deep learning career. So it's time to apply what you've learned so far in this deep learning course. Your final project is to take some real-world data, we talked about this in the ethics lecture actually, of masses detected in mammograms, and just based on the measurements of those masses, see if you can predict whether they are benign or malignant. So we have a data set of mammogram masses that were detected in real people, and we've had real doctors look at those and determine whether or not they are benign or malignant in nature. So let's see if you can set up a neural network of your own that can successfully classify whether these masses are benign or malignant in nature. Let's dive in. So I've given you some data and a template to work from at least. The data that we're going to be working with is in your course materials. The mammographic_masses.data.txt file is the raw data that you'll be using to train your model with. And you can see it's just 6 columns of stuff. What do those things represent? Well, I'll show you in a minute. There's actually a description of this data set in the names.txt file here that goes along with that data set. But to get you started, I've given you a little bit of a template to work with. If you open up the deep learning project.ipynb file, that will give you something to work from and describe the nature of the data that I'm throwing at you. All right. So this came from the UCI repository, and I gave you a little bit of a link to where the original data came from. That's actually a great resource for finding other data to play with. So if you're still learning machine learning, that's a great place to find stuff to mess around with and experiment with. But for this example, that's the one we're going to be messing with. So here's the description of those 6 columns. One is called the BI-RADS assessment, and that's basically a measurement of how confident our diagnosis was of this particular mass. Now that's sort of giving away the answer. It's not what we call a predictive attribute, so we're not going to actually use that for training our model. Next, we have the patient's age. We have a classification of the shape of the mass. We have a classification of the mass margin, how it looks like, the density of the mass. And finally, we have the thing that we're trying to predict. So this is the label, the severity, whether it's benign, 0, or malignant, 1. So we have what's here a binary classification problem, very similar to stuff that we've done earlier in the course, and you shouldn't need much more than to use code snippets from earlier exercises in this course and adapting them to this data set. Okay, now one little caveat here. Typically when you're doing machine learning, you don't want to deal with what we call nominal data, and both shape and margin are technically nominal data. While we're converting them to numbers, those numbers aren't necessarily meaningful in terms of their gradation. You know, going from 1 to 4 doesn't mean that we're increasingly going from 1 to round to irregular in a linear fashion. But sometimes you have to make do with what you have. It's better than nothing. And at least there is some logic to the progression of numerical scores here to these descriptions. So they do generally go from more regular to more irregular as those numbers increase. So we're going to go ahead and use those anyway. This is important stuff. You know, there's a lot of unnecessary anguish and surgery that comes along from false positives on mammograms. So if you can build a better way of diagnosing these things, all the better. But again, think back to my ethics lecture. You don't want to oversell this. You want to make sure this is just a tool that might be used for a real human doctor, unless you're very confident that the system can actually outperform a human. And by definition, it can't, because we're training this on data that was created by humans. So how could it possibly be better than a human? Think about that. All right, so your job is to build a multi-layer perceptron to classify these things. I was able to get over 80% accuracy with mine. Let's see how you can do. Now, a lot of the work is just going to be in cleaning the data, and I'll step you through the things you need to do here. So start by importing the data file using the read CSV function. You can then take a look at that, convert the missing data into knot of numbers, and make sure you import all the column names. You might need to clean the data, so try to get an idea of the nature of the data by using describe on your resulting pandas data frame. Next, you'll need to drop rows that have missing data, and once you've taken care of that, you need to convert the data frames into NumPy arrays that you can then pass into scikit-learn or into Keras. Okay? So you also need to normalize the data before you analyze it with Keras. So a little hint there is to use preprocessing.standardscaler out of sklearn. That can make things very easy for you. That's the one thing that we haven't really done before. The rest of this you should be able to figure out just based on previous examples. Once you have the data in the proper format, it's then pretty straightforward to build an MLP model using Keras, and you can experiment with different topologies, different hyperparameters, and see how well you can do. So I'm going to set you loose here and give this a shot. Let's see how you do. When you come back in the next lecture, I'll show you my solution and how I walk through this myself. So go forth and practice what you've learned. So I hope you got some good experience there in actually applying what you learned to create a neural network that can classify masses found in mammograms as benign or malignant. Like I said, I got around 80% accuracy myself. I wonder how you did. If you want to compare your implementation to mine, go ahead and open up the Deep Learning Project-Solution Python notebook file there in your course materials, and you can take a peek at how I did it. You'll see that it's pretty much just rehashing code that we've looked at in previous examples, just applying it to a different data set, so I hope you weren't too challenged by it, but you probably also use this as another reminder that a lot of the work that you do in practice is just cleaning your data and preparing it, and not so much actually analyzing it. So that is the reality of machine learning. Anyway, I started off by just blindly reading in the CSV file using pd.readcsv and taking a look at it. And I saw at that point that the column names were wrong. There was missing column name information in the data file, and there were missing values in there that were indicated by question marks. So have to read that in a little bit more intelligently. So on my second try here, I called read CSV, passing in explicitly the knowledge that question marks mean missing values, or NA values. And I passed in an array of column names like we did before, and did another head on the resulting pandas data frame, and things look a lot better now. At that point, we have to clean the data now that it's in a proper format and organized properly. We can do a describe on that to take a look at things and get an idea that we are missing some data, and things seem to be reasonably well distributed at least. At this point, we did a little count here to see what exactly is missing. So my strategy here was to see if there's any sort of bias that I'm going to introduce by actually removing missing values. And if I were to see that the missing data seems to be randomly distributed, just by eyeballing it at least, that's probably a good indication that it's safe to just go ahead and drop those missing rows. So given that I've determined that that is an okay thing to do, I've gone ahead and called drop NA on that data frame and described it. And now I can see that I do have the same number of counts of rows in each individual column. So I now have a complete data set where I've thrown out rows that are missing data. And I've convinced myself that's an okay thing to do statistically. All right, so now we need to actually extract the features and values that we want to feed into our model, our neural network. So I've extracted the feature data, the age, shape, margin, and density, from that data frame and extracted that into a NumPy array called all features. I've also extracted the severity column and converted that to an all classes array that I can pass in as my label data. And I've also created a handy dandy array of column names since I'll need that later on. So just to visualize, I've punched in all features just to take a look at what that looks like. And sure enough, looks legitimate. Looks like an array of 4 features apiece on each row. Looks reasonable. At that point, I need to scale my data down. So to do that, all I need to do is import the preprocessing.standardScaler function there and apply that to my feature data. And if I look at all features scaled that came out of that transformation, I can see that everything appears to be normally distributed now, centered around 0 and with a standard deviation of 1, which is what we want. Remember, when you're putting inputs into a neural network, it's important that your data is normalized before you put it in. Now we get to the actual meat of the thing, actually setting up our MLP model, and I'm going to wrap this in such a way that I can use scikit-learn's cross-val score to evaluate its performance. So in my example here, I've created a little function called createModel that creates a sequential model, adds in a dense layer with 6 units or 6 neurons using the ReLU activation function. I've added in another layer with 1 that does my final sigmoid classification, my binary classification on top of that. And I've compiled that with the RMS prop optimizer and the binary cross entropy loss function. So with this, we've set up a single layer of 6 neurons that feeds into one final binary classification layer. Very simple. And I've then gone ahead and used the Keras classifier to build a scikit-learn compatible version of this neural network, and I've passed that into cross-val score to actually do k-fold cross-validation, in this case with 10 folds, and print out the results. So, with just these 6 neurons, I was able to achieve an 80% accuracy in correctly predicting whether or not a mass was benign or malignant just based on the measurements of that mass. Now, in the real world, doctors use a lot more information than just those measurements, so our algorithm is kind of at a disadvantage compared to those human doctors to begin with, but that's not too bad. If you did better, if you used more layers, more neurons, I'd be curious to see if you actually got a better result. It turns out that sometimes you don't need a whole lot to actually get the optimal result from the data that you have. But if you were able to substantially improve upon that result, congratulations. So I hope deep learning has been demystified for you. And up next, we'll talk about how to continue learning more in the field of deep learning. Well, I hope I've whet your appetite on deep learning and you're eager to learn more. It's a very quickly emerging field and a relatively new one, so traditional resources for learning are still a little bit hard to find. There's a few other online courses out there about it like this one, but as far as books go, O'Reilly's a pretty good bet. I've liked this one a lot. I don't make any money from this, by the way. I'm not like recommending this to like make a buck. I just actually like this book. It's called Hands-On Machine Learning with Scikit-Learn and TensorFlow. It sticks at the TensorFlow level, so like we talked about, it's more of a lower level implementation. It doesn't get into Keras much at all, but it is a good overview of the theory behind the different techniques of neural networks and RNNs and CNNs and whatnot. So if you want a little bit of a supplementary print material to reinforce what you learned in this course, I think it's a pretty good bet. There's also a new book that just came out, I'm talking in the fall of 2017 here, called Deep Learning, just came out from O'Reilly. It's also good. It's different though in that it actually uses Java, so it's not using Python at all, or the TensorFlow library or the Keras library. Instead, it's using the DL4J library. So if you actually prefer Java over Python, this might be a very good book to pick up. Also goes over the general concepts that we talked about here in a little bit more depth as well. Cool. And remember, Google is your friend if there's some specific thing you're trying to figure out, like how do I use a GRU cell in Keras? Well, just punch that into Google and it will probably come up with some tutorials and documentation at least of how to do that. Google, again, is your friend in this stuff because this stuff is always changing, and if you want up-to-the-date information, that's going to have the most up-to-the-date resources for you available. Cool, so go forth and do more deep learning. Hey, I hope you enjoyed this video and maybe learned a thing or three. If you'd like to learn more with me, please check out the link in the description below. I have a whole larger course on data science, deep learning, and machine learning with Python there. It's very popular and highly rated, so I hope you'll check it out. And you'll also get a really nice discount on it by using that link in the description there. Anyway, thanks for watching, and I hope to see you again soon.